light carries a secret that most people never learn about. Beyond its symmetries, beyond its wave-particle duality, photons possess something called angular momentum, a hidden spinning property that changes how light behaves in ways that seem almost magical. Tonight, we'll explore this forgotten aspect of light step by step, using real quantum mechanics, laboratory measurements, and the precise physics that govern how photons twist through space and time. It's a story of invisible spirals, orbital states that shouldn't exist, and electromagnetic fields that dance in patterns more complex than we ever imagined. We'll see how this property lets light carry information in entirely new ways, manipulate matter at the atomic level, and even create beams that heal themselves when blocked. If this gentle journey into quantum optics helps you discover something beautiful about our universe, your quiet like, your soft subscription, and your thoughtful comments mean everything. Now, let's step into the spiral world of light's hidden spin. What happens when scientists discover that light has been keeping secrets from us for billions of years? On a cold February evening in 1992 at Leiden University in the Netherlands, physicist Les Allen peered through his microscope at something that would fundamentally change our understanding of reality itself. The laser beam dancing before his eyes wasn't behaving like any light he had ever encountered. Instead of the familiar bright circular spot that textbooks promised, Allen witnessed something extraordinary. Perfect rings of luminous energy arranged in concentric circles, each surrounding a mysterious dark void at the center. His colleagues gathered around the laboratory bench, their breath visible in the chilled air, as they attempted to comprehend what nature was revealing. The patterns resembled cosmic donuts, ethereal smoke rings frozen in time, or perhaps the fingerprints of some invisible force that had touched light itself. Traditional optical theory suggested this should be impossible. Every equation, every principle they had learned, predicted that coherent laser light would form simple Gaussian profiles, those bell-shaped intensity distributions that had dominated optics for decades. Yet here before them lay evidence of something far more sophisticated, far more elegant than anyone had imagined. The light possessed structure, intention, a kind of hidden choreography that seemed to dance according to rules written in a language physicists were only beginning to decipher. Allen's team rotated polarizing filters, adjusted focusing lenses, and modified their experimental setup, but the mysterious patterns persisted with unwavering consistency. The donut shapes weren't artifacts or experimental errors. They were fundamental features of this strange new form of light. Each ring told a story of helical wavefronts spiraling through space like cosmic corkscrews, carrying energy and momentum in ways that defied conventional wisdom. The researchers realized they were witnessing the birth of a new chapter in physics, one where light could twist and swirl with the same complexity that matter exhibited in quantum mechanical systems. Word spread quickly through the international physics community as Allen and his colleagues documented their findings. The paper they would publish in Physical Review A that year contained mathematical expressions that looked almost alive, complex exponential functions with azimuthal phase factors that wrapped around themselves in infinite spirals. These weren't just pretty mathematical curiosities. They represented a fundamental property of electromagnetic radiation that had somehow escaped detection for over a century since Maxwell first wrote his famous equations. The implications began cascading through Allen's mind like dominoes falling in precise sequence. If light could carry this hidden form of angular momentum entirely separate from the familiar spin associated with polarization, then photons possessed degrees of freedom that opened doorways to technologies not yet dreamed. The team worked through the night, brewing endless cups of coffee as they performed calculation after calculation, each confirming what their eyes had already witnessed. Light, that most fundamental messenger of the universe, had been carrying encrypted information in its twisted structure since the first stars ignited. Every photon streaming from distant galaxies, every beam of sunlight warming their faces, every laser pulse in their laboratory contained the potential for infinite complexity hidden within its helical embrace. The mathematical beauty of their discovery resonated with the deepest symmetries of nature, connecting electromagnetic waves to the quantum mechanical orbitals that electrons occupy around atomic nuclei. Allen's team had uncovered a universal language that nature used across all scales, from the microscopic quantum realm to the vast cosmic theatre where light travels between stars. Their laboratory had become a portal through which humanity glimpsed one of the universe's most elegant secrets, a secret that light had been whispering for eons to anyone patient enough to listen with the right instruments and open enough to accept that reality contained mysteries far more wonderful than fiction could ever imagine. How can something simultaneously rotate and remain perfectly motionless, defying every intuition about movement and stillness? As Alan's team adjusted their detection equipment that transformative evening, the luminous patterns before them revealed geometric perfection that seemed almost supernatural in its precision. The Laguerre Gaussian beam profiles displayed concentric rings of brilliant intensity, each circle nested within the next like Russian dolls made of pure energy, all surrounding that enigmatic central darkness where photons simply refused to exist. This wasn't mere absence of illumination at the core. It represented a fundamental singularity in the electromagnetic field, a point where the mathematical description of light itself broke down and demanded entirely new physics to explain its behavior. The wavefronts themselves told an even more astonishing story as the researchers traced their helical architecture through space and time. Each surface of constant phase twisted through 3 dimensions like an infinite cosmic corkscrew, spiraling endlessly forward at the speed of light while maintaining its structural integrity across vast distances. The mathematical elegance underlying this phenomenon emerged through the exponential function exp times I times m times phi, where the azimuthal angle phi wrapped around the beam axis and the integer m determined how many times the phase completed a full rotation in one circumnavigation of the central void. This topological charge m became the key to understanding why these beams possessed such remarkable stability and why they carried fundamentally different properties than ordinary light. When m equaled 0, the familiar Gaussian beam appeared with its simple circular cross-section and uniform phase across any transverse plane. But as m increased to 1, 2, 3, or any positive integer, the central darkness expanded and the surrounding rings grew more complex, each configuration carrying increasing amounts of this mysterious orbital angular momentum. Negative values of m created patterns that spiraled in the opposite direction, their helical wavefronts corkscrewing backwards through space while maintaining the same ring-like intensity distributions. The profound realization struck the research team like lightning, illuminating a vast landscape previously hidden in darkness. Each ring of radiant energy was rotating, even while appearing completely stationary to their instruments. The rotation wasn't mechanical motion of matter, but rather a fundamental twist in the electromagnetic field itself, a property as intrinsic to these photons as their frequency or wavelength. Time seemed suspended in the laboratory as the scientists grappled with implications that challenged their deepest assumptions about the nature of light and motion. These weren't just theoretical curiosities confined to academic discussions. They represented a completely new degree of freedom for electromagnetic radiation, a hidden dimension of complexity that could potentially revolutionize everything from communications to quantum computing. The team realized they were witnessing the electromagnetic analog of electron orbitals in atoms, where quantum mechanical wave functions also exhibited similar phase structures and angular momentum properties. Nature, it seemed, had embedded the same mathematical principles across multiple scales of reality, from subatomic particles to macroscopic light beams. Each photon in their twisted beam carried quantized units of orbital angular momentum, measured in multiples of the reduced Planck constant, making these classical electromagnetic waves behave with quantum mechanical precision. The helical phase fronts meant that any cross-sectional slice through the beam revealed phase values that increased linearly around the azimuthal direction, jumping discontinuously from 2π back to 0 at one specific radial line extending from the central singularity. This phase discontinuity created the characteristic fork pattern when the beam interfered with a reference wave, providing experimenters with a direct method to measure the topological charge and confirm the theoretical predictions. As dawn approached and exhaustion began affecting their concentration, Alan's team understood they had discovered something that would echo through decades of future research, opening pathways to technologies not yet imagined and answering questions about light that nobody had even thought to ask until that remarkable February night when nature revealed one of its most beautiful and profound secrets. Could it be that photons and electrons, separated by vast differences in scale and behavior, actually follow the same fundamental choreography written into the fabric of reality itself. The breakthrough that would forever change physics crystallized when Allen's research group recognized the mathematical signatures they were observing in their twisted light beams perfectly mirrored the quantum mechanical descriptions of atomic orbitals that had puzzled scientists since the early 20th century. Each individual photon racing through their experimental apparatus carried exactly L times h bar units of orbital angular momentum, where L represented the topological charge integer and h bar symbolized the reduced Planck constant that governs all quantum phenomena. This quantization wasn't approximate or emergent, it was absolute and fundamental, revealing that electromagnetic radiation obeyed the same discrete rules that confined electrons to specific energy levels around atomic nuclei. The parallel became impossible to ignore as the team compared their experimental data with textbook illustrations of electron probability clouds surrounding hydrogen atoms. The familiar p orbitals with their dumbbell shapes, the more complex d orbitals resembling four-leaf clovers, and the intricate f orbitals with their multiple lobes all exhibited the same helical phase structures and angular momentum properties that now danced before them in macroscopic beams of laser light. Nature had apparently embedded identical mathematical principles across scales forms spanning many orders of magnitude, from the quantum realm where electrons orbit atomic cores to the classical domain where electromagnetic waves propagate through free space. This universality suggested something profound about the underlying architecture of physical law, hinting that angular momentum represented a fundamental currency of the cosmos, traded and conserved across all interactions, with mathematical precision. The realization struck the laboratory like thunder rolling across clear skies. Light could be twisted just like matter, carrying information and energy in helical configurations that defied classical intuition, while obeying quantum mechanical rules with exquisite accuracy. Decades of assuming that photons were simple, structureless particles suddenly seemed naive, as the evidence mounted that these massless messengers possessed rich internal complexity, capable of encoding vast amounts of information in their twisted wavefronts. The quantum connection extended even deeper when the researchers calculated how many distinct orbital angular momentum states could theoretically exist within a single beam of coherent light. Unlike electron orbitals, which were limited by the Coulomb potential binding them to atomic nuclei, photon orbitals faced no such restrictions. The topological charge L could assume any integer value from negative infinity to positive infinity, creating an infinite dimensional Hilbert space where information could be encoded with unlimited density. Each photon became a potential carrier of arbitrary amounts of data, limited only by practical considerations of detection and measurement rather than fundamental physical constraints. The implications cascaded through multiple branches of physics simultaneously as the team realized their discovery connected quantum mechanics, classical electromagnetism, and information theory in previously unimaginable ways. Quantum entanglement experiments could now explore correlations between particles separated not just by distance but by the infinite ladder of orbital angular momentum states, each rung offering new possibilities for secure communication and quantum computing applications. The laboratory had become a window into the quantum world, where photons revealed their hidden complexity through patterns that human eyes could actually observe and measure. These weren't abstract, mathematical constructions confined to theoretical discussions. They were tangible, reproducible phenomena that demonstrated how quantum mechanics manifested itself in the macroscopic world of everyday experience. Allen's team understood they had witnessed the emergence of a new paradigm where light served as a bridge between the mysterious quantum realm and the familiar classical universe, carrying quantum information encoded in observable intensity patterns and measurable phase relationships. The profound beauty of this discovery lay not just in its scientific significance, but in its revelation that nature had been hiding this elegant secret for billions of years, waiting patiently for human curiosity and ingenuity to develop the tools necessary to decode its message. Every sunrise, every rainbow, every star twinkling in the night sky had been broadcasting this information through twisted photons that carried the signatures of quantum mechanical perfection across the vast emptiness of space, whispering secrets about the fundamental structure of reality to anyone with eyes to see and minds prepared to understand the language of helical light dancing through the infinite cosmos surrounding our small blue planet. What if everything we thought we understood about how light spins through space represents only half the story, leaving an entire universe of rotational possibilities hidden from our perception until now? Take a slow breath as we explore how photons can dance in two completely different ways, beginning with the familiar choreography that scientists have recognized since James Clerk Maxwell first penned his revolutionary equations in the 1860s. Circular polarization embodies the intrinsic spin, angular momentum that every physicist learns during their undergraduate studies, a fundamental property where the electric field vector traces elegant helical paths through space as electromagnetic waves propagate at light speeds toward distant destinations. This spin, angular momentum, manifests itself when photons carry exactly plus or minus 1 unit of reduced Planck, constant worth of rotational energy, depending on whether their polarization follows right-handed or left-handed circular patterns around the direction of propagation. The physical meaning becomes crystal clear when we visualize the electric field vector as a cosmic needle, constantly rotating in either clockwise or counterclockwise directions, while the entire wave packet rushes forward through the vacuum of space. Right-handed circular polarization corresponds to positive spin angular momentum, where an observer looking toward the approaching light source would see the electric field rotating clockwise, like the hands of a traditional timepiece. Conversely, left-handed circular polarization carries negative spin angular momentum, with the electric field vector spinning counterclockwise in what appears to reverse the natural flow of time itself. This intrinsic spinning behavior differs fundamentally from any mechanical rotation we might observe in everyday experience, representing instead a pure electromagnetic phenomenon, where the field itself twists through dimensions that exist beyond our normal three-dimensional intuition. The historical context reveals how deeply this property penetrates into the foundations of modern physics, having been embedded within Maxwell's electromagnetic theory from its very inception over 150 years ago. Early researchers recognized that linearly polarized light could be decomposed into equal superpositions of right and left circular components, each carrying opposite angular momentum that cancelled perfectly to produce zero net spin. The analogy between a spinning bullet and a spinning drill bit illuminates the distinction between ordinary mechanical rotation and this more fundamental electromagnetic spinning. A bullet fired from a rifled barrel spins around its axis of motion while travelling in a straight line, maintaining its rotational energy as a separate degree of freedom independent of its forward momentum. Similarly, circularly polarized photons carry intrinsic spin that exists independently of their linear momentum, creating a dual nature where each quantum of light simultaneously rushes forward and rotates around itself with quantum mechanical precision. However, unlike bullets or drill bits, photons possess no mass and therefore cannot spin in the conventional sense that applies to material objects. Their spin represents a purely field-based phenomenon arising from the vector nature of electromagnetic radiation, where the electric and magnetic components oscillate perpendicular to each other and to the direction of propagation. This creates a three-dimensional dance of intersecting sinusoidal waves that naturally gives rise to the helical trajectories we observe in circularly polarized light. The conservation of angular momentum plays a crucial role in understanding how photons interact with matter, particularly in atomic transitions where electrons absorb or emit electromagnetic radiation. When atoms undergo quantum jumps between energy levels with different angular momentum quantum numbers, the difference must be carried away by the photons themselves, ensuring that the total angular momentum of the combined system remains constant throughout the interaction. This principle enables techniques like optical pumping, where circularly polarized light selectively excites atomic transitions to create population imbalances that form the basis for laser operation and magnetic resonance imaging. The remarkable stability of photon spin over cosmic distances allows astronomers to probe the magnetic fields of distant stars and galaxies by analyzing the polarization of their emitted radiation. Light that began its journey billions of years ago from quasars at the edge of the observable universe still carries the signature of its original spin state, providing a window into the electromagnetic environments that existed when the cosmos was young and galaxies were first forming from primordial gas clouds. Why did nature choose to hide an infinite ladder of rotational states within ordinary beams of light, waiting billions of years for human consciousness to discover this secret dimension of electromagnetic complexity? The orbital angular momentum that Allen's team discovered represents something far more exotic and powerful than the familiar spin we just explored, emerging not from the polarization of individual photons, but from the helical phase structure that shapes entire wavefronts as they spiral through space like cosmic DNA molecules encoding information in their twisted geometry. Unlike the intrinsic spin-angular momentum limited to plus or minus 1 unit per photon, orbital angular momentum breaks free from all constraints, allowing the topological charge L to assume any integer value, stretching from negative infinity through 0 to positive infinity in an endless sequence of possible states. This mathematical freedom creates a truly unlimited information space where each photon can carry L times h bar worth of orbital angular momentum, with no theoretical upper bound on how much rotational energy can be encoded within a single quantum of electromagnetic radiation. The profound difference between these two forms of angular momentum becomes clear through a crucial insight that revolutionizes our understanding of light itself. While polarization spins individual photons around their own axes like microscopic tops, orbital angular momentum spins entire beam patterns around the central propagation axis like galactic spirals rotating through the cosmos. This distinction separates local properties that affect each photon independently from global properties that emerge from the collective behavior of countless electromagnetic field oscillations working together to create macroscopic patterns visible to human observers. The helical phase structure responsible for orbital angular momentum arises when different parts of a wavefront carry different phase values that change systematically as we move around the beam circumference. Instead of all points at the same distance from the center oscillating in the perfect synchrony, the electromagnetic field develops a twist where the phase advances or retards smoothly as we circle the beam axis, completing exactly L full rotations for each complete trip around the central singularity. This creates wavefronts that resemble infinite spiral staircases climbing through space and time, with each step representing a specific phase relationship that must be maintained with quantum mechanical precision to preserve the orbital angular momentum. The topological nature of this charge provides extraordinary stability against perturbations that would normally destroy delicate quantum states through decoherence and environmental interference. Small obstacles, atmospheric turbulence, or imperfect optical components cannot eliminate the fundamental twist in the wavefront, because doing so would require cutting the helical structure and reconnecting it with different topology, a process forbidden by the continuous nature of electromagnetic fields. This robustness makes orbital angular momentum states ideal for long-distance communication through free space or optical fibers, where maintaining quantum information becomes increasingly challenging as propagation distances extend across continents or between satellites orbiting in the vacuum of space. The unlimited nature of possible topological charges opens doorways to communication protocols with exponentially expanded capacity compared to traditional binary systems restricted to two states. While conventional digital technology encodes information using sequences of zeros and ones, orbital angular momentum allows each photon to carry labels from an infinite alphabet where negative integers spiral clockwise, positive integers spiral counterclockwise, and 0 represents the familiar Gaussian beam without any helical structure. Theoretical calculations suggest that properly designed systems could pack hundreds or thousands of independent data channels into the same optical bandwidth that previously carried only a single stream of information, multiplying communication capacity without requiring additional spectrum allocation or more powerful transmitters. The mathematical elegance underlying this phenomenon connects orbital angular momentum to fundamental symmetries in nature, particularly the rotational symmetry that governs everything from planetary orbits to atomic structure. The same conservation laws that prevent satellites from spontaneously changing their orbital parameters also protect the topological charge of light beams from random fluctuations, ensuring that information encoded in helical wavefronts remains intact throughout its journey from transmitter to receiver. Recent experimental demonstrations have pushed the boundaries of what seemed possible just decades ago, creating light beams carrying topological charges exceeding 10,000 and maintaining their orbital angular momentum across distances spanning hundreds of kilometers through the atmosphere, or thousands of kilometers through optical fibers designed specifically to support these exotic electromagnetic modes. How can a single beam of light simultaneously carry two completely independent forms of angular momentum, each operating according to different rules while occupying the same physical space and time. The fundamental difference between spin and orbital angular momentum reveals one of nature's most elegant design principles, where electromagnetic radiation exploits multiple dimensions of rotational freedom to maximize its information-carrying capacity beyond anything our ancestors could have imagined when they first began studying the behavior of sunbeams and candlelight. Spin angular momentum faces strict quantum mechanical limitations that confine each photon to exactly +1 or -1 unit of rotational energy, creating a binary system where only two possible states exist, regardless of the beam's intensity, frequency, or any other parameter we might adjust in our laboratories. This constraint emerges from the fundamental vector nature of electromagnetic fields and the requirement that photons remain massless while travelling at the ultimate speed limit imposed by relativity theory. Conversely, orbital angular momentum breaks free from all such restrictions, allowing the topological charge to explore every integer on the infinite number line from the most negative values our imaginations can conceive to the most positive numbers our mathematics can describe. This unlimited freedom transforms each photon into a potential vessel for arbitrary amounts of information, constrained only by practical considerations of generation, transmission, and detection rather than fundamental laws of physics. The independence of these two angular momentum types creates possibilities that seemed like pure fantasy until recent experimental breakthroughs confirmed their reality through precise measurements and controlled demonstrations. A single light beam can simultaneously exhibit right-handed circular polarization, carrying positive spin angular momentum, while also possessing a helical wavefront structure with topological charge equal to +7, creating a hybrid state where individual photons spin clockwise around themselves while the entire beam pattern rotates counterclockwise around the central propagation axis. This dual rotation operates without interference or conflict because spin affects the local oscillation directions of electric and magnetic field vectors, while orbital angular momentum governs the global phase relationships that determine how different parts of the wavefront relate to each other across the beam's cross-section. Recent research published in Frontiers in Physics during 2023 addressed one of the most challenging theoretical problems in modern optics: how to separate spin and orbital contributions to the total angular momentum in a gauge-invariant manner that produces physically meaningful results independent of mathematical coordinate choices. The breakthrough emerged from recognizing that while individual components might appear arbitrary depending on our reference frame selection, the observable consequences of angular momentum transfer to material objects remain absolute and measurable through carefully designed experiments involving optomechanical interactions. This theoretical progress cleared the path for practical applications by resolving fundamental ambiguities that had plagued researchers for decades, ensuring that orbital angular momentum could be harnessed with confidence for real-world technologies requiring precision and reliability. The profound implications extend far beyond academic curiosity into realms where infinite dimensional information spaces reshape our understanding of what becomes possible when intelligence meets electromagnetic radiation enhanced with unlimited rotational complexity. Classical communication systems struggled with the fundamental trade-off between data transmission rates and error correction overhead, forcing engineers to choose between speed and reliability when designing networks for global internet infrastructure. Orbital angular momentum eliminates this compromise by providing exponentially more communication channels within the same spectral bandwidth, allowing simultaneous transmission of thousands of independent data streams while maintaining the error correction capacity needed for fault-tolerant quantum computing applications. Light suddenly transformed from a simple carrier of energy propagating between sources and detectors into a carrier of infinite complexity capable of encoding arbitrary amounts of information within the helical structures of its twisted wavefronts. This metamorphosis opens doorways to technologies that seemed impossible under the constraints of traditional binary systems, where computational power scaled linearly with the number of physical components rather than exponentially with the sophistication of information encoding techniques. Quantum computers exploiting high-dimensional orbital angular momentum states could potentially solve certain categories of problems exponentially faster than any classical machine, while communication networks utilizing multiple topological charges simultaneously could support the bandwidth requirements of entire civilizations without requiring additional spectrum allocation from regulatory authorities. The convergence of spin and orbital angular momentum in practical devices promises to revolutionize fields ranging from medical imaging to astronomical observations, where the ability to encode and decode complex information patterns within individual photons enables unprecedented sensitivity and resolution in measurements that probe the deepest mysteries of biological processes and cosmic evolution across scales, spanning from molecular interactions to galactic dynamics. What mathematical language did nature choose to describe the infinite complexity hidden within twisted beams of light? And why does this cosmic grammar follow such elegant rules that human minds can decipher its deepest secrets? Now we enter the elegant mathematical world that describes these spiraling photons through a family of functions so beautiful and precise that they seem almost too perfect to emerge from the chaotic complexity of electromagnetic field equations. The Laguerre-Gaussian modes, denoted by the notation Lg subscript p superscript EIL, represent exact analytical solutions to the paraxial wave equation that governs how light propagates through free space under conditions where the beam remains, approximately parallel to its main direction of travel. Each mode carries two distinct quantum numbers that completely specify its unique identity. The radial index p counts the number of concentric bright rings surrounding the central darkness, while the azimuthal index L determines the topological charge that creates the helical twist in the wavefront structure. These indices work together like coordinates on a map, allowing scientists to navigate through the infinite landscape of possible beam configurations with mathematical precision and experimental reproducibility. The radial index p begins at 0 for the simplest case where only a single bright ring exists around the central void, then increases by integer steps to create increasingly complex patterns with multiple concentric rings separated by regions of zero intensity where destructive interference cancels the electromagnetic fields completely. Meanwhile, the azimuthal index L can assume any positive or negative integer value, with larger absolute values creating more tightly wound helical structures that carry correspondingly greater amounts of orbital angular momentum according to the fundamental relationship discovered by Allen's research team. The physical meaning encoded within these mathematical symbols reveals itself when we examine actual beam profiles produced in carefully controlled laboratory experiments. A mode designated Lg subscript 0 superscript 1 exhibits a single bright ring with topological charge equal to positive 1, creating a donut-shaped intensity distribution with a helical wavefront that completes exactly one full rotation around the beam axis during each complete circuit of the central singularity. Increasing the radial index to Lg subscript 1 superscript 1 adds a second concentric ring outside the first, while maintaining the same helical twist characterized by the unchanged azimuthal index. The beautiful fact that these patterns represent exact solutions to the wave equation rather than approximate descriptions or numerical simulations demonstrates the profound mathematical harmony underlying all electromagnetic phenomena into the universe. Unlike many physics problems that require computer calculations to achieve even rough accuracy, the Laguerre-Gaussian modes can be written down analytically using elementary functions involving exponentials, polynomials, and trigonometric expressions that undergraduate students can manipulate by hand using techniques learned in standard calculus courses. This mathematical elegance suggests that nature operates according to principles of beauty and simplicity that transcend the apparent complexity of physical phenomena, revealing hidden symmetries that connect electromagnetic radiation to the deepest structures of space and time itself. The orthogonality property provides perhaps the most remarkable feature of this mathematical framework, ensuring that different Laguerre-Gaussian modes behave like independent channels that never interfere with each other even when they propagate through the same region of space simultaneously. Two beams with different radial indices, different azimuthal indices, or any combination of distinct quantum numbers will pass through each other without exchanging energy or creating interference patterns that might corrupt the information carried by either mode. This orthogonality emerges naturally from the mathematical structure of the wave equation solutions, reflecting fundamental symmetries in the underlying physics, rather than accidental coincidences or approximate relationships that break down under extreme conditions. The practical implications of this mathematical perfection enable communication systems that exploit multiple orbital angular momentum modes simultaneously, transmitting independent data streams through the same optical fiber or free space channel without crosstalk or signal degradation that would compromise information fidelity. Each mode functions like a unique musical note in light's infinite symphony, maintaining its distinct identity while contributing to the overall harmonic structure that emerges when multiple modes combine to create complex electromagnetic compositions. The mathematical beauty extends beyond practical applications into realms where pure science reveals the aesthetic principles that govern natural phenomena, suggesting that the universe operates according to rules that satisfy both logical necessity and artistic perfection in ways that continue to inspire wonder among researchers who dedicate their careers to understanding how mathematics and physics interweave to create the reality we observe through our instruments and experience through our senses. If this gentle exploration of light's mathematical secrets brings you peace, or sparks curiosity about the elegant equations governing our universe, a quiet light helps support our journey through science together. Could there exist a mathematical point in space where light simply refuses to exist, protected by laws so fundamental that no force in the universe can illuminate this eternal darkness? The phase singularity represents one of nature's most profound mysteries, a location where the electromagnetic field amplitude drops to exactly zero and remains there regardless of how much energy we attempt to focus into that forbidden region. This central vortex creates an absolute void within the brightness, not through absorption or scattering, but through a more fundamental mechanism where the mathematical description of light itself becomes undefined and the normal rules of optics cease to apply. Unlike temporary shadows cast by physical objects that block illumination, the phase singularity emerges from the wave nature of light itself, arising when electromagnetic fields oscillating in different directions around a circular path interfere destructively with perfect precision. The topological protection surrounding this phenomenon ensures that small perturbations, atmospheric turbulence, or imperfect optical components cannot eliminate the central darkness, because doing so would require fundamentally altering the mathematical topology of the electromagnetic field configuration. Imagine trying to remove a knot from a rope without cutting the rope or sliding the ends through the loop. The topological constraints make certain transformations impossible regardless of how cleverly we manipulate the system. Similarly, the phase singularity maintains its existence through topological invariance that connects it to deep principles in mathematical physics governing everything from quantum field theory to general relativity. As we trace a complete circle around this mysterious void, the phase of the electromagnetic field winds smoothly from 0 radians through 2 pi times L radians before returning to its starting value, where L represents the topological charge that determines how many complete rotations the phase undergoes during one trip around the singularity. This phase progression resembles climbing a spiral staircase where each step corresponds to a specific angular position around the central axis, and the total height gained after one complete circuit depends on how many times the staircase wraps around itself before returning to ground level. For a beam with topological charge equal to positive 2 and 2, the phase completes exactly 2 full rotations during one journey around the singularity, creating a double helix structure in the electromagnetic field that carries twice as much orbital angular momentum as a simple single-charge vortex. The experimental signature of phase singularities reveals itself through interference patterns that exhibit characteristic fork-like dislocations when the vortex beam combines with a reference wave having uniform phase across its cross-section. These fork patterns appear wherever the helical wavefront intersects the plane reference wave, creating discontinuities in the interference fringes that directly indicate the presence and strength of the topological charge. Counting the number of fork prongs provides an immediate measurement of the absolute value of L, while the direction of the fork opening reveals whether the charge is positive or negative according to the handedness of the helical twist. Advanced interferometric techniques exploit these signatures to analyze complex superpositions containing multiple singularities with different charges, enabling researchers to decompose arbitrary beam patterns into their constituent Laguerre Gaussian components with remarkable precision. The connection to similar vortices in other physical systems demonstrates the universal nature of topological phenomena across vastly different scales and energy regimes throughout the natural world. Superfluids like liquid helium below the lambda transition temperature exhibit quantized circulation around vortex cores where the density drops to 0 and the quantum mechanical wave function becomes undefined, creating persistent current loops that can maintain their circulation for indefinite periods without energy dissipation. Bose-Einstein condensates formed from ultra-cold atomic gases display analogous behavior when stirred by carefully designed laser beams, generating quantized vortices that trap atoms in orbital motion around central regions devoid of matter. These parallels suggest that phase singularities represent fundamental features of wave physics that transcend the specific details of electromagnetic radiation, quantum fluids, or atomic gases, revealing universal mathematical structures that govern how waves can twist and curl through space while maintaining their coherent properties. Recent experiments have created optical vortices carrying topological charges exceeding 10,000, demonstrating the remarkable stability of these singularities even under extreme conditions that would destroy most. Other delicate quantum states through decoherence and environmental interference, proving that nature has embedded robust information storage mechanisms within the very fabric of light itself. Why must nature force us to choose between the information-carrying capacity of twisted light and our ability to focus that same light into the smallest possible spots? And what ingenious solutions have engineers developed to overcome this fundamental limitation? The beam quality parameter known as m² provides a universal metric for quantifying how closely any given light beam approximates the perfect focusing behavior of an ideal Gaussian mode, with higher values indicating increasingly poor performance in applications requiring tight concentration of optical energy. The mathematical relationship m² equals 2 times p plus the absolute value of L plus 1 reveals the inexorable trade-off between orbital angular momentum content and focusing capability, where p represents the radial mode index counting concentric rings and L denotes the topological charge responsible for the helical phase structure. This equation demonstrates that every additional unit of orbital angular momentum, or every extra ring in the intensity pattern, degrades the beam quality by exactly 1 unit, creating a fundamental tension between information capacity and optical performance that engineers must navigate when designing practical systems. The physical origin of this trade-off emerges from the wave nature of light itself, where modes carrying orbital angular momentum necessarily spread their energy across larger transverse areas to accommodate the complex intensity patterns and phase structures required to maintain their helical wave fronts. Unlike the fundamental Gaussian mode that concentrates all its energy in a smooth central peak with m² equal to exactly 1, higher-order Laguerre Gaussian modes distribute their power among multiple concentric rings separated by regions of zero intensity where the electromagnetic fields cancel through destructive interference. This distributed energy pattern prevents efficient focusing because optical systems can only concentrate light that approaches the lens or mirror in nearly parallel rays. But orbital angular momentum modes arrive with complex wavefront curvatures and phase gradients that resist compression into tight focal spots. The engineering challenge of maintaining mode purity over extended propagation distances compounds these fundamental limitations as atmospheric turbulence, fiber imperfections, and thermal fluctuations gradually corrupt the delicate phase relationships that preserve orbital angular momentum during transmission. Even minor perturbations can couple energy between different Laguerre Gaussian modes, causing a pure input beam to evolve into a complex superposition of multiple modes with degraded information fidelity and further reduced beam quality. Traditional optical FEs, designed for fundamental mode propagation, actively suppress higher-order modes through their refractive index profiles, making long-distance transmission of orbital angular momentum virtually impossible until researchers developed specialized designs that support multiple modes simultaneously. The breakthrough came through careful engineering of the fiber geometry and refractive index distribution to create separate channels for different orbital angular momentum states, preventing mode mixing while maintaining acceptable propagation losses over practical transmission distances. Recent advances published in Nature Communications during 2019 demonstrated successful transmission of multiple orbital angular momentum modes through specially designed optical fibers spanning hundreds of kilometers without significant crosstalk or signal degradation. These achievements required precise control of fiber manufacturing tolerances, environmental stability, and launch conditions to maintain the delicate phase relationships necessary for preserving orbital angular momentum throughout the transmission link. The research teams employed sophisticated mode multiplexing and demultiplexing techniques to combine multiple information channels into single fibers and subsequently separate them at the receiver without introducing errors that would compromise data integrity. Advanced signal processing algorithms compensated for residual mode coupling and atmospheric effects that inevitably occur in real-world transmission environments, enabling practical deployment of orbital angular momentum communication systems for applications ranging from high-capacity internet backbone connections to secure quantum communication networks. The development of integrated photonic circuits capable of generating, manipulating, and detecting orbital angular momentum modes on silicon chips promises to revolutionize the field by eliminating many of the bulk optical components that currently limit system performance and increase costs. These miniaturized devices exploit the same physical principles as their free space counterparts, but implement them using lithographically defined waveguides and resonators that can be mass-produced using semiconductor fabrication techniques borrowed from the electronics industry. The resulting systems achieve unprecedented stability and reproducibility while reducing power consumption and footprint requirements that previously made orbital angular momentum technology impractical for widespread deployment in telecommunications infrastructure and consumer electronics applications. What extraordinary precision would be required to carve invisible staircases into transparent materials, creating helical pathways that guide photons along predetermined spiral trajectories with nanometer accuracy? Let's discover the ingenious ways scientists learn to twist light on command, beginning with the elegant spiral phase plates that pioneered the practical generation of orbital angular momentum beams through purely mechanical means that seem almost impossibly simple yet achieve breathtaking optical sophistication. These remarkable devices consist of transparent glass or crystalline materials carefully machined into three-dimensional spiral structures where the thickness varies continuously around the circumference, creating a helical surface that resembles a microscopic parking garage ramp frozen in clear solid matter. Each complete revolution around the central axis corresponds to one full step in this optical staircase, where the additional material thickness introduces exactly 2 pi radians of phase delay relative to the thinnest region of the plate. The physical mechanism operates through the fundamental relationship between material thickness and optical path length, exploiting the fact that light travels more slowly through dense transparent media than through vacuum or air, causing electromagnetic waves to accumulate additional phase as they traverse regions of increased thickness. Engineers calculate the precise spiral geometry by determining how much extra material must be added at each angular position to create the desired phase progression, accounting for the wavelength of the incident light and the refractive index of the substrate material. The manufacturing process requires extraordinary precision because errors in thickness of even a few nanometers can introduce phase errors that corrupt the orbital angular momentum generation and create unwanted diffraction patterns that contaminate the output beam. Advanced fabrication techniques borrowed from semiconductor manufacturing enable the creation of spiral phase plates with tolerances measured in atomic scale dimensions, using processes like electron beam lithography, reactive ion etching, and precision diamond turning to achieve the required surface quality and dimensional accuracy. The resulting devices exhibit remarkable simplicity in operation, requiring no electrical power, computer control or active feedback systems to transform ordinary Gaussian laser beams into twisted vortex modes with well-defined topological charges. Users simply place the spiral phase plate in the path of a collimated laser beam and immediately observe the characteristic donut-shaped intensity pattern that indicates successful orbital angular momentum generation. The analogy of carving staircases for light to walk up in spirals captures the essential physics while revealing the almost architectural nature of these optical elements, where electromagnetic waves follow predetermined paths through three-dimensional structures designed with the same careful attention to geometry and proportion that architects apply to buildings intended for human occupation. However, these elegant devices suffer from fundamental limitations that restrict their versatility and practical applications in modern optical systems, requiring flexibility and adaptability. The most significant constraint emerges from their fixed topological charge, determined permanently by the spiral geometry etched into the substrate during manufacturing. Once fabricated, a spiral phase plate can generate only one specific orbital angular momentum value, preventing dynamic control or real-time switching between different vortex modes that many applications require. Users needing multiple topological charges must maintain collections of different plates and manually exchange them in their optical setups, introducing mechanical complexity and alignment challenges that limit system performance and operational convenience. The wavelength dependence presents another serious limitation, because the phase delay introduced by any given thickness depends on the ratio between the material optical path and the wavelength of the incident light. Spiral phase plates designed for red laser light at 650 nanometers will produce incorrect phase relationships when illuminated, with blue light at 450 nanometers causing degraded orbital angular momentum purity and unwanted spatial mode mixing that corrupts the output beam quality. This chromatic limitation prevents the use of spiral phase plates in broadband applications or systems requiring operation across multiple wavelengths simultaneously, forcing designers to seek alternative generation methods that offer greater spectral flexibility. Despite these constraints, spiral phase plates continue serving important roles in research laboratories and specialized applications where their simplicity, reliability, and excellent mode purity outweigh their inflexibility, particularly in situations requiring stable orbital angular momentum generation over extended periods without maintenance or recalibration. How did computer screens evolve into programmable windows that can reshape light itself, transforming digital patterns into physical optical vortices with the same ease that monitors display photographs or videos? The digital holography revolution emerged when researchers realized that spatial light modulators, essentially sophisticated liquid crystal displays capable of controlling both amplitude and phase, could generate arbitrary orbital angular momentum states by displaying computer-calculated interference patterns that diffract incident laser beams into desired helical configurations. These remarkable devices consist of millions of individually controllable pixels, each acting as a miniature optical element that can introduce specific phase delays or amplitude modifications to the electromagnetic waves passing through or reflecting from its surface. Computer-generated holograms replace the fixed spiral structures of phase plates with dynamic digital patterns that can be updated in real time, enabling researchers to switch between different topological charges, create superpositions of multiple vortex modes, or generate entirely new beam configurations simply by uploading different data files to the spatial light modulator. The flexibility of this approach revolutionized orbital angular momentum research by eliminating the need for extensive collections of custom-fabricated optical elements, replacing entire laboratories filled with specialized components with single devices capable of performing countless different functions under the software control. The fundamental physics underlying digital holography relies on diffraction phenomena that occur when coherent light encounters periodic structures with feature sizes comparable to the optical wavelength. Computer algorithms calculate the precise pixel patterns required to create specific diffraction orders carrying desired orbital angular momentum values, taking into account the wavelength of the incident radiation, the pixel size and spacing of the spatial light modulator, and the desired intensity and phase distributions in the output beam. These calculations often involve sophisticated optimization techniques that minimize unwanted diffraction orders while maximizing the efficiency of energy transfer into the target mode, balancing multiple competing requirements through iterative numerical procedures that can require substantial computational resources for complex beam configurations. Fork patterns represent the most common and recognizable type of computer-generated hologram used for orbital angular momentum generation, appearing as binary gratings where the interference fringes split into characteristic Y-shaped structures that directly indicate the topological charge of the resulting vortex beam. The number of fork prongs corresponds exactly to the absolute value of the desired orbital angular momentum. Quantum number. While the orientation of the fork opening determines whether the charge is positive or negative according to conventions established by the international optics community, these patterns exploit the mathematical relationship between helical phase, structures and their Fourier transforms, creating spatial frequencies that generate the required orbital angular momentum through well-understood principles of wave optics and diffraction theory. Real-time control capabilities enable dynamic experiments impossible with static optical elements, allowing researchers to study the temporal evolution of orbital angular momentum states, investigate nonlinear optical processes involving vortex beams, or implement adaptive optical systems that compensate for atmospheric turbulence or other environmental perturbations. Modern spatial light modulators can update their displayed patterns at rates exceeding several kilohertz, fast enough to track rapid changes in experimental conditions or implement closed-loop control systems that maintain optimal beam quality despite varying external influences. This temporal flexibility proves essential for applications in optical communication systems, where different data channels require different orbital angular momentum modes, quantum optics experiments involving time-varying entanglement protocols, or industrial laser processing applications where beam shaping requirements change according to material properties or manufacturing specifications. However, efficiency limitations present significant challenges that prevent digital holography from achieving the same performance levels as optimized static elements in many practical applications. Typical spatial light modulators convert only 20 to 40% of the incident laser power into the desired diffraction order, with the remaining energy distributed among unwanted orders that represent wasted power and potential sources of noise or interference. This low efficiency stems from the discrete pixel structure of the devices, which creates periodic diffraction gratings that inevitably generate multiple orders simultaneously, and from the limited phase modulation range available with liquid crystal technology, which rarely exceeds 2p radians and often falls short of this theoretical maximum due to practical engineering constraints. Unwanted diffraction orders carry significant fractions of the total optical power while possessing different orbital angular momentum values or propagation directions that can interfere with the intended application, requiring careful beam filtering or spatial mode cleaning techniques that further reduce system efficiency and increase complexity. Could engineers design materials that exist in the liminal space between 2 and 3 dimensions, creating surfaces so thin they're practically invisible, yet powerful enough to completely reshape the fundamental properties of light passing through them? The metasurface revolution represents perhaps the most extraordinary advancement in orbital angular momentum generation, emerging from a 2019 breakthrough where researchers demonstrated that single planar structures composed of carefully arranged nanoscale elements could create arbitrary vortex states with efficiency and versatility previously thought impossible using conventional optical components. These metamaterials operate through an entirely different physical principle than traditional optics, exploiting the resonant properties of subwavelength antennas to control electromagnetic fields at scales far smaller than the wavelength of visible light itself. Each metasurface consists of thousands or millions of these tiny antennas, each one smaller than bacteria, yet precisely engineered to interact with specific polarization states and wavelengths of incident radiation. The nanoscale antennas function as individual phase-shifting elements that can introduce arbitrary local modifications to the electromagnetic wavefront, creating complex spatial patterns of phase and amplitude that would require bulky lens systems or multiple optical elements to achieve using classical approaches. The engineering principles underlying metasurface design borrow heavily from radiofrequency antenna theory, adapted and miniaturized to operate at optical frequencies where wavelengths measure hundreds of nanometers rather than meters or centimeters. Researchers carefully tune the size, shape, orientation, and spacing of each photons antenna element to achieve specific scattering properties that collectively produce the desired optical transformation when thousands of these elements work together across the surface area of the device. Advanced electromagnetic simulation software enables designers to predict and optimize the performance of complex metasurface patterns before fabrication, accounting for near-field coupling between adjacent antennas, substrate effects, and manufacturing tolerances that can affect the final device performance. The fabrication process relies on semiconductor lithography techniques originally developed for microprocessor manufacturing, using electron beam writing or deep ultraviolet photolithography to define antenna patterns with nanometer precisions across wafer-scale areas. The resulting devices exhibit remarkable thinness, typically measuring less than 1 wavelength in total thickness while achieving optical transformations that would traditionally require centimeters or meters of conventional optical elements. This dramatic size reduction enables integration into compact systems where space and weight constraints preclude the use of bulky refractive or diffractive components, opening pathways to portable orbital angular momentum generation systems for field applications or consumer electronics. Recent 2025 developments published in Nature Photonics demonstrated integrated quantum vortex emitters that combine metasurface technology with on-chip photon sources to create complete orbital angular momentum generation systems fabricated on silicon substrates using standard semiconductor processing techniques. These integrated devices eliminate the need for external laser sources and bulk optical alignment, creating self-contained vortex generators that can be mass-produced using established manufacturing infrastructure. The quantum nature of the generated light enables applications in secure communication protocols and quantum computing architectures that exploit the infinite-dimensional Hilbert space associated with orbital angular momentum states. The precision required to fabricate these devices challenges the limits of current manufacturing technology, requiring atomic-scale control over feature dimensions and positioning to achieve the theoretical performance predicted by electromagnetic simulations. Even small deviations from the intended antenna geometry can introduce phase errors that degrade the orbital angular momentum purity or reduce the conversion efficiency, necessitating sophisticated quality control procedures and statistical characterization of large device populations. However, the benefits of metasurface technology far outweigh these manufacturing challenges, particularly for the applications requiring dynamic control over multiple orbital angular momentum states simultaneously. Advanced metasurfaces incorporate tunable elements such as liquid crystals, phase change materials, or electro-optic polymers that enable real-time reconfiguration of the antenna properties under electrical or optical control. This tunability allows single devices to generate different topological charges, switch between various beam profiles, or adapt their optical response to changing environmental conditions without mechanical movement or component replacement. The combination of extreme miniaturization, design flexibility, and dynamic control capabilities positions metasurfaces as the enabling technology for next-generation optical systems that integrate orbital angular momentum functionality into applications ranging from augmented reality displays to satellite communication terminals, demonstrating how fundamental advances in nanoscale engineering can revolutionize macroscopic technologies and enable entirely new categories of optical devices. What if we could convince laser cavities themselves to naturally emit twisted light, eliminating the need for external conversion devices and producing orbital angular momentum directly from the quantum mechanical processes that create coherent photons? Direct laser generation represents the ultimate goal in vortex beam technology, where carefully engineered optical resonators produce helical modes as their fundamental operating states, rather than requiring post-processing of conventional Gaussian outputs through phase plates or spatial light modulators. This approach promises unprecedented mode purity because the orbital angular momentum emerges from the laser physics itself, arising naturally from the electromagnetic field configurations that achieve lowest loss and highest gain within the specially designed cavity geometry. Traditional laser resonators favor fundamental Gaussian modes because these configurations provide optimal overlap with typical gain media and minimize diffraction losses at mirrors and apertures, but researchers have discovered that appropriate modifications to cavity design can instead promote higher-order Laguerre-Gaussian modes while suppressing unwanted fundamental mode oscillation. The key insight involves engineering the transverse mode structure through careful control of mirror curvatures, cavity length ratios, and intracavity elements that selectively enhance the gain experienced by desired orbital angular momentum states, while introducing losses for competing modes. Photonic crystal surface-emitting lasers represent one of the most promising implementations of this concept, utilizing two-dimensional periodic structures etched into semiconductor substrates to create distributed feedback that naturally supports vortex modes with predetermined topological charges. Research published in 2023 demonstrated successful generation of pure Laguerre-Gaussian modes with topological charges up to plus and minus 2 using these devices, achieving output powers comparable to conventional laser diodes while maintaining excellent beam quality and orbital angular momentum purity. The photonic crystal approach exploits the band gap properties of periodic dielectric structures to control which electromagnetic modes can propagate within the laser cavity, essentially programming the allowed solutions to the wave equation through careful design of the crystal lattice geometry and refractive index modulation. Engineers can tailor the photonic band structure to exhibit gaps that suppress fundamental modes while providing guided propagation for specific orbital angular momentum states, creating laser cavities that naturally prefer twisted light over conventional circular beams. The semiconductor gain medium provides optical amplification through stimulated emission processes that occur when electrically injected carriers recombine across the band gap, generating photons with energies determined by the material composition and quantum well structure. By integrating the photonic crystal pattern directly into the semiconductor surface, researchers eliminate the need for separate optical elements while achieving precise control over mode selection and beam shaping within the active laser medium itself. The primary advantage of direct generation lies in achieving superior mode purity compared to conversion-based approaches that inevitably introduce some contamination from unwanted spatial modes or diffraction artifacts. Laser cavities operating in pure Laguerre Gaussian modes produce output beams with well-defined topological charges and excellent phase coherence across the entire aperture, characteristics that prove essential for applications requiring high-fidelity orbital angular momentum, states such as quantum communication or precision interferometry. Additionally, direct generation eliminates conversion losses associated with external beam shaping devices, potentially achieving higher overall system efficiency while reducing complexity and cost for commercial applications. However, significant challenges remain in achieving stable single-mode operation and preventing mode competition that can degrade orbital angular momentum purity or cause temporal instabilities in the output beam characteristics. Laser cavities supporting multiple transverse modes often exhibit competition between different spatial configurations, leading to mode hopping or simultaneous oscillation of several modes that creates complex beating patterns and temporal fluctuations in the output intensity and phase structure. The gain bandwidth of typical semiconductor materials can simultaneously support numerous orbital angular momentum states with similar threshold conditions, making it difficult to maintain pure single-mode operation without additional mode selection mechanisms. Thermal effects, mechanical vibrations, and current injection non-uniformities can all perturb the delicate balance required for stable vortex mode operation, causing the laser to switch between different topological charges or revert to fundamental mode oscillation under varying operating conditions. Advanced feedback control systems and sophisticated cavity designs incorporating mode filters or nonlinear saturable absorbers show promise for achieving robust single-mode performance, but these solutions often compromise the simplicity and compactness that make direct generation attractive for practical applications requiring reliable orbital angular momentum sources. How can two particles of light become so intimately connected that measuring one instantly determines the fate of its partner across the universe? And what happens when each particle carries not just two possible outcomes, but an infinite spectrum of quantum possibilities? Here, we witness how quantum mechanics and orbital angular momentum create new possibilities that transcend every limitation imposed by traditional two-level quantum systems, opening doorways to computational and communication technologies that seemed like pure science fiction until researchers began exploring the vast landscape of high-dimensional entanglement. Traditional quantum information processing relies on qubits that exist in superpositions of two fundamental states, typically represented as 0 and 1 in mathematical notation, creating binary systems where each particle carries exactly one bit of classical information or one qubit of quantum information, depending on whether superposition and entanglement effects are exploited. This binary constraint emerged naturally from the spin-spin properties of the electrons or the polarization states of photons, physical systems where only two orthogonal configurations exist and intermediate states represent quantum superpositions rather than additional discrete possibilities. However, orbital angular momentum shatters this limitation by providing access to an unlimited alphabet of quantum states labeled by the integer, values of the topological charge that can range from negative infinity through 0 to positive infinity without any fundamental restrictions. Each orbital angular momentum eigenstate corresponds to a different helical configuration of the electromagnetic field, creating a quantum mechanical ladder where adjacent rungs differ by exactly one unit of angular momentum, and the spacing between levels remains uniform regardless of how high we climb toward larger topological charges. This infinite dimensional Hilbert space transforms single photons into carriers of arbitrary amounts of quantum information, limited only by practical considerations of generation, transmission, and detection, rather than fundamental laws of physics that constrain traditional qubit systems. The revolutionary experiment performed by Anton Zeilinger's research group in 2016 demonstrated entanglement between photon pairs, where individual particles carried orbital angular momentum states with absolute topological charges exceeding 10,000. creating quantum correlations across a range of possibilities that dwarfs any previous achievement in quantum information science. These experiments required extraordinary precision in both state preparation and measurement, using sophisticated optical systems capable of generating, maintaining, and detecting orbital angular momentum entanglement while preserving quantum coherence across enormous ranges of topological charge values. The technical challenges included developing detection methods sensitive enough to resolve individual orbital angular momentum states among thousands of possibilities while maintaining sufficient efficiency to observe quantum correlations above classical statistical fluctuations. Specialized mode sorters and holographic analyzers enabled researchers to project the high-dimensional entangled states onto specific orbital angular momentum eigenstates, measuring coincidence rates that confirmed genuine quantum entanglement rather than classical correlations that could arise from common source fluctuations or other mundane effects. The exponential increase in information capacity achieved through high-dimensional orbital angular momentum entanglement revolutionizes quantum communication protocols by enabling transmission of multiple bits of information per photon, rather than the single-bit limitation imposed by traditional polarization-based systems. Each measurement of an entangled photon's topological charge can yield log base 2 of the total number of accessible states worth of information, meaning that systems supporting 100 orbital angular momentum levels provide more than 6 bits of information per photon, while systems accessing 10,000 levels exceed 13 bits per photon. This dramatic enhancement in information density enables quantum cryptographic protocols with exponentially improved security levels, quantum computing algorithms with reduced resource requirements, and quantum sensing applications with enhanced precision through exploitation of high-dimensional quantum correlations. The physical picture of 2 photons, each carrying the signature of infinity encoded within their helical wavefront structures, captures the profound beauty and mysterious nature of quantum entanglement enhanced by orbital angular momentum degrees of freedom. These particles maintain perfect correlations across arbitrary distances, despite possessing access to unlimited numbers of possible measurement outcomes, creating a quantum mechanical dance where measuring one photon's topological charge instantly determines the probability distributions for all possible results of measurements performed on its distant partner. The implications extend far beyond practical applications into fundamental questions about the nature of reality itself, suggesting that the universe may contain hidden dimensions of correlation and information storage that dwarf our current understanding of space, time, and causality. Could nature have designed orbital angular momentum specifically to solve the fundamental challenges of quantum communication across vast distances through chaotic atmospheric conditions that would normally destroy delicate quantum states? Free space quantum key distribution using orbital angular momentum has emerged as one of the most promising solutions for secure communication networks that must operate through open air rather than protected fiber optic cables. Exploiting the unique properties of twisted light to maintain quantum correlations despite atmospheric turbulence, scattering, and other environmental perturbations that plague conventional approaches. The breakthrough came when researchers realized that orbital angular momentum states possess inherent stability against many forms of noise that typically destroy quantum entanglement during long-distance transmission, particularly the phase fluctuations and beam-wandering effects caused by temperature gradients and pressure variations in the Earth's atmosphere. Unlike polarization-based quantum communication systems that rely on maintaining precise alignment between linear or circular polarization states, orbital angular momentum protocols can tolerate significant misalignments and rotations without compromising the fundamental quantum correlations needed for secure key distribution. The rotation-invariant twisted photon protocols developed in 2014 represented a paradigm shift in quantum communication strategy, recognizing that certain combinations of orbital angular momentum states remain perfectly correlated even when the entire beam undergoes arbitrary rotation around the propagation axis during transmission. These protocols exploit the mathematical structure of orbital angular momentum to create entangled states where measuring one photon in a rotated reference frame still provides complete information about its partner's quantum state, eliminating the need for active stabilization systems that would otherwise be required to maintain alignment between transmitter and receiver over intercontinental distances. The key insight involves encoding information in relative phase relationships between different orbital angular momentum components rather than absolute values of individual topological charges, creating a form of differential encoding that remains robust against global phase shifts and rotational perturbations. Recent satellite-based demonstrations have validated the practical feasibility of orbital angular momentum quantum communication across the most challenging transmission environments imaginable, where signals must traverse hundreds of kilometers through the dynamic atmospheric boundary layer before reaching orbital receivers equipped with specialized detection systems. These experiments required unprecedented coordination between ground-based transmitters and space-based receivers, accounting for Doppler shifts caused by orbital motion, pointing accuracy requirements that exceed conventional satellite communication standards, and the extreme photon flux limitations imposed by quantum communication protocols that typically operate with single photon detection rates. The success of these demonstrations proved that orbital angular momentum maintains its quantum properties even under conditions where conventional approaches would fail completely, opening pathways to global quantum internet infrastructure based on satellite relay networks rather than terrestrial fiber connections. The resistance to atmospheric turbulence stems from the distributed nature of orbital angular momentum states, which spread their quantum information across the entire transverse profile of the beam, rather than concentrating everything in a single localized region vulnerable to scintillation effects. When atmospheric cells create local, phase distortions or intensity fluctuations, the orbital angular momentum information remains recoverable because the helical structure contains redundancy that enables reconstruction of the original quantum state even when significant portions of the beam experience corruption. This robustness contrasts sharply with polarization-based systems, where any rotation of the polarization vector can completely scramble the encoded quantum information, requiring complex adaptive optic systems to maintain signal fidelity. Advanced error correction protocols specifically designed for orbital angular momentum quantum communication exploit the high-dimensional nature of the state space to implement quantum error correction codes with superior performance compared to traditional approaches limited to two-dimensional qubit systems. The security advantages of high-dimensional spaces provide exponentially enhanced protection against eavesdropping attempts compared to conventional quantum keys, distribution protocols operating with polarization qubits. Any attempt to intercept and to measure orbital angular momentum quantum states necessarily disturbs the transmission in ways that are statistically detectable by the legitimate parties. But the vast number of possible measurement outcomes makes it computationally infeasible for adversaries to extract useful information, even if they successfully intercept portions of the quantum transmission. The mathematical complexity of high-dimensional quantum state spaces creates natural cryptographic protection that scales exponentially with the number of accessible orbital angular momentum modes, ensuring that quantum communication security improves automatically as technology advances enable access to higher topological charges and more sophisticated encoding schemes that exploit the infinite dimensional Hilbert space associated with twisted light beams carrying unlimited amounts of orbital angular momentum. How do you measure something that's spinning at light speed while simultaneously existing in a quantum superposition of infinite possible rotational states? And what ingenious detection schemes have physicists developed to capture the full complexity of twisted photons without destroying their delicate quantum properties? The measurement challenge represents one of the most fascinating puzzles in orbital angular momentum research, requiring detection techniques that can simultaneously determine both the amplitude and phase relationships of electromagnetic fields oscillating at frequencies approaching a petahertz, while preserving the quantum mechanical coherence essential for information processing applications. Traditional photodiodes and cameras detect only intensity patterns, completely ignoring the phase information that encodes orbital angular momentum, forcing researchers to develop sophisticated interferometric methods that convert invisible phase structures into measurable intensity variations through controlled interference with reference beams having known phase profiles. Mode sorters emerged as the first practical solution to this detection challenge, utilizing carefully designed optical systems that spatially separate different orbital angular momentum components of an incident beam into distinct output channels, where conventional detectors can measure their individual intensities. These devices exploit the orthogonality properties of Laguerre Gaussian modes to create linear transformations that map each input topological charge to a specific spatial location in the output plane, essentially functioning as optical prisms that disperse orbital angular momentum rather than wavelength or polarization. The mathematical foundation underlying mode sorters involves unitary transformations that preserve the total photon number while redistributing the spatial distribution according to the orbital angular momentum content, enabling simultaneous measurement of multiple modes without introducing crosstalk or measurement artifacts that would corrupt the quantum information. Holographic techniques provide an alternative approach that leverages computer-generated interference patterns to selectively couple incident orbital angular momentum modes to specific diffraction orders, creating programmable detection systems that can be rapidly reconfigured to measure different sets of topological charges by simply updating the displayed hologram patterns. These methods exploit the same physical principles used for orbital angular momentum generation, but operate in reverse, using known holographic patterns to analyze unknown input states rather than transforming known input states into desired output configurations. Advanced holographic detectors incorporate spatial light modulators that can display different analysis patterns for each measurement, enabling rapid switching between various detection bases that reveal different aspects of the quantum state under investigation. The recent breakthrough published in Nature Communications during 2019 demonstrated successful sorting of hundreds of orbital angular momentum modes simultaneously using a single integrated photonic device, achieving unprecedented efficiency and channel capacity that opens pathways to practical high-dimensional quantum communication systems. This achievement required solving complex engineering challenges related to crosstalk between adjacent modes, insertion losses that would otherwise limit detection sensitivity, and fabrication tolerances that must be maintained across large arrays of closely spaced optical elements. The device architecture exploited cascaded interferometric structures that progressively separate different orbital angular momentum components through multiple stages of binary mode splitting, creating a tree-like network where each branch corresponds to a specific topological charge range, and the final outputs provide direct measurement of individual mode amplitudes. Quantum tomography of orbital angular momentum states extends these measurement concepts to completely characterize unknown quantum systems by performing measurements in multiple complementary bases that together provide sufficient information to reconstruct the full density matrix describing the quantum state. This process requires measuring expectation values of numerous operators that span the orbital angular momentum state space, typically involving projections onto different linear combinations of eigenstates that reveal both diagonal and off-diagonal elements of the density matrix through statistical analysis of large numbers of measurement results. The mathematical complexity of high-dimensional quantum tomography grows exponentially with the number of accessible orbital angular momentum modes, requiring sophisticated optimization algorithms and statistical analysis techniques to extract meaningful information from experimental data, while accounting for measurement noise and systematic errors. The beautiful uncertainty principle governing angular position and angular momentum creates fundamental limits on measurement precision that reflect deep connections between classical mechanics and quantum mechanics in rotational systems. This principle states that the product of uncertainties in angular position and orbital angular momentum must exceed a minimum value determined by Planck's constant, ensuring that perfect knowledge of one quantity necessarily implies complete ignorance about its conjugate variable. The implications extend beyond fundamental physics into practical constraints on measurement protocols that must balance the precision of orbital angular momentum determination against the corresponding loss of phase information, creating trade-offs that influence the design of quantum communication systems and quantum computing architectures, exploiting orbital angular momentum degrees of freedom. Could the internet itself be fundamentally transformed by teaching light how to carry multiple independent conversations simultaneously through the same fiber optic cable, each conversation encoded in a different helical twist that never interferes with its neighbors? Tonight, we explore how this forgotten property is reshaping technology as orbital angular momentum multiplexing emerges as the key to breaking through the bandwidth limitations that threaten to strangle global communications networks, struggling to keep pace with exponentially growing data demands from video streaming, cloud computing, and emerging applications requiring unprecedented information transfer rates. The fundamental principle behind this revolution lies in exploiting the infinite orthogonal channels provided by different topological charges, where each orbital angular momentum mode can carry completely independent data streams without crosstalk or interference, even when all modes propagate through exactly the same physical medium. Traditional wavelength division. Multiplexing approaches this concept by using different colours of light to create parallel channels, but the electromagnetic spectrum provides only limited numbers of usable wavelengths before neighbouring channels begin overlapping and corrupting each other's signals. Orbital angular momentum multiplexing transcends these spectral limitations by operating within any single wavelength, creating virtually unlimited communication channels constrained only by practical considerations of mode generation, transmission, and detection, rather than fundamental physical limits on available bandwidth. The transformative 2013 breakthrough demonstrated terabit-scale transmission using orbital angular momentum, achieving data rates exceeding 1 terabit per second, by simultaneously transmitting independent information streams across multiple topological charge channels while maintaining signal quality sufficient for error-free communication. This achievement required developing sophisticated, multiplexing hardware capable of generating multiple orbital angular momentum modes simultaneously, combining them into single beams for transmission, and subsequently separating them at the receiver without introducing crosstalk that would corrupt the encoded data. The experimental demonstration utilized both free space propagation and specially designed optical fibers optimized to support multiple orbital angular momentum modes without significant mode coupling or differential attenuation that would degrade channel isolation. Each beam of light suddenly became capable of carrying not one message but hundreds simultaneously, transforming optical communication from a single-lane highway into a massively parallel superhighway, where information flows through multiple independent lanes, operating at light speed. Fiber optic challenges initially seemed insurmountable because conventional telecommunications fibers were designed specifically to suppress higher-order modes and maintain single-mode propagation, making them incompatible with orbital angular momentum multiplexing applications that require preserving multiple spatial modes throughout long-distance transmission links. The circular symmetry breaking introduced by bends, stress, and in manufacturing imperfections in standard fibers causes orbital angular momentum modes to couple into each other, creating crosstalk that destroys channel isolation and renders multiplexing ineffective for practical communication systems. However, recent solutions have emerged through careful engineering of specialized fiber designs that maintain the cylindrical symmetry essential for preserving orbital angular momentum during propagation while providing sufficiently low loss for practical telecommunications applications. Ring core fibers represent one promising approach, utilizing annular refractive index profiles that guide light in hollow, cylindrical regions where orbital angular momentum modes can propagate without experiencing the symmetry-breaking effects that plague solid core designs. Multi-core fibers offer an alternative strategy that dedicates separate cores to different orbital angular momentum modes, preventing mode coupling while enabling parallel transmission of multiple channels through single cable assemblies. Free space communication advantages become particularly compelling for applications where fiber installation proves impractical or impossible, such as satellite links, emergency communications networks, or connections between buildings separated by geographical obstacles that preclude cable installation. Atmospheric propagation naturally preserves orbital angular momentum over distances spanning hundreds of kilometers, enabling high-capacity wireless links that exploit the same multiplexing principles used in fiber systems, while avoiding the infrastructure costs and installation challenges associated with cable networks. Military and emergency response applications benefit enormously from these capabilities, providing secure high-bandwidth communications that remain operational when terrestrial infrastructure becomes compromised or unavailable. The scalability of orbital angular momentum multiplexing promises continued capacity expansion as technology advances enable access to higher-order modes and more sophisticated signal processing techniques that can maintain channel isolation across increasingly large numbers of parallel data streams, suggesting that this approach could support communication requirements far into the future without requiring fundamental changes to network architecture or transmission protocols. What forces could be gentle enough to grasp individual living cells without damage, yet powerful enough to spin microscopic machines with precision measured in nanometers? And how has twisted light become the ultimate tool for manipulating matter at scales where traditional mechanical devices simply cannot operate? Optical tweezers enhanced. with orbital angular momentum have revolutionized our ability to control microscopic objects by exploiting the mechanical torque that emerges when twisted photons transfer their angular momentum to material particles, creating optical spanners that can rotate trapped objects with exquisite control while simultaneously holding them in precise three-dimensional positions. The fundamental physics underlying this manipulation relies on conservation of angular momentum during light-matter interactions, where photons carrying orbital angular momentum must transfer their rotational energy to any particle that absorbs or scatters them, resulting in measurable mechanical forces and torques that can overcome Brownian motion and gravitational effects at microscopic scales. Unlike conventional optical tweezers that provide only translational control through radiation pressure gradients, orbital angular momentum beams add rotational degrees of freedom that enable complete six-dimensional, manipulation of trapped particles, including both position and orientation control. The intensity gradients associated with the characteristic donut-shaped beam profiles create stable trapping potentials that confine particles near the central region where electromagnetic field gradients are strongest, while the helical phase structure ensures that scattered photons carry away angular momentum in a manner that induces compensating rotation in the trapped object. Micromotor demonstrations have showcased the remarkable precision achievable through orbital angular momentum manipulation, creating rotating systems where microscopic particles serve as components in optically driven mechanical devices operating at scales far below anything achievable with conventional manufacturing techniques. Researchers have successfully trapped and rotated particles ranging from dielectric spheres and metallic nanoparticles to complex biological structures including bacteria, viruses, and subcellular organelles, demonstrating that optical angular momentum transfer works effectively across diverse material compositions and size ranges. The torque magnitude depends on both the topological charge of the trapping beam and the optical properties of the trapped particle, enabling selective manipulation of different objects within heterogeneous samples by choosing appropriate beam parameters that optimize the coupling efficiency for specific particle types while minimizing unwanted effects on neighboring structures. Cell manipulation and rotation applications have opened entirely new research directions in biology and medicine by providing non-invasive methods for studying cellular mechanics, investigating membrane dynamics, and analyzing intracellular transport processes that were previously inaccessible to experimental investigation. Living cells can be trapped and rotated without apparent damage, allowing researchers to examine all sides of three-dimensional cellular structures or, 2, apply controlled mechanical stresses that reveal information about cell wall elasticity, membrane tension, and cytoskeletal organization. The ability to rotate cells at controlled speeds enables time-resolved studies of dynamic processes such as cell division, organelle migration, and protein trafficking that require observation from multiple viewing angles to understand the full three-dimensional nature of biological phenomena. Recent applications in medicine have explored the potential for orbital angular momentum optical tweezers to serve as tools for microsurgery, drug delivery, and diagnostic applications where precise manipulation of biological materials at the cellular level could enable new therapeutic approaches. Cancer research has benefited particularly from these capabilities, allowing scientists to isolate and study individual tumor cells, investigate metastatic behavior, and test potential treatments at the single-cell level with unprecedented precision and control. Optomechanical measurement techniques demonstrated in Science Advances during 2016 have achieved remarkable sensitivity in detecting photon angular momentum transfer, enabling quantitative studies of the fundamental processes underlying optical manipulation, while validating theoretical predictions about electromagnetic momentum, conservation in complex optical systems. These measurements required developing detection schemes sensitive enough to resolve individual photon momentum transfer events, while maintaining sufficient temporal resolution to track dynamic processes occurring on microsecond timescales. The experimental apparatus combined high-resolution position sensing with torque measurement capabilities that could detect angular momentum changes corresponding to individual photon absorption or scattering events, providing direct confirmation of the quantum mechanical nature of optical angular momentum transfer in macroscopic mechanical systems. Advanced applications now under development include optical assembly of three-dimensional microstructures, where multiple trapped particles can be positioned and oriented with nanometer precision to create complex mechanical devices or biological constructs that would be impossible to fabricate using conventional techniques. The prospect of optically powered molecular machines driven by orbital angular momentum suggests future applications in nanotechnology, drug delivery, and cellular engineering that could revolutionize medicine by providing tools for manipulation and control at the most fundamental scales of biological organization. How can we force light to reveal details smaller than its own wavelength, defying fundamental limits that have constrained microscopy for over a century? And what happens when we twist that light into helical vortices that carry additional information about the structures they illuminate? Super-resolution microscopy enhanced with orbital angular momentum has emerged as one of the most transformative developments in biological imaging, creating light that can see smaller than it should be able to through clever exploitation of nonlinear optical phenomena and structured illumination techniques that circumvent classical diffraction barriers. The revolutionary approach known as stimulated emission depletion microscopy, or SETED, achieves unprecedented resolution by using orbital angular momentum beams to create depletion patterns that selectively turn off fluorescence everywhere except in nanoscale regions much smaller than the diffraction-limited spot size that normally constrains optical resolution. The fundamental principle exploits the donut-shaped intensity profile characteristic of orbital angular momentum modes, where the central zero creates a region of minimal depletion surrounded by intense illumination that effectively quenches fluorescence through stimulated emission processes. By carefully overlapping excitation and depletion beams, researchers can confine active fluorescence to volumes approaching molecular dimensions, while maintaining the gentleness and specificity that make fluorescence microscopy ideal for studying living biological systems without the damage associated with electron beam techniques. Breaking diffraction limits with twisted light represents a paradigm shift from traditional approaches that accepted the Rayleigh criterion as an insurmountable barrier to optical resolution, replacing passive acceptance of physical limitations with active engineering of electromagnetic field distributions that exploit nonlinear interactions between light and matter. The helical phase structure of orbital angular momentum beams provides additional degrees of freedom for controlling the spatial distribution of optical intensity, enabling creation of depletion patterns with features much smaller than the wavelength of the light itself. Recent theoretical work has shown that higher-order orbital angular momentum modes can generate increasingly complex depletion patterns with multiple zeros and sophisticated spatial structures that enable simultaneous multi-point super-resolution imaging or enhanced three-dimensional sectioning capabilities. The topological protection of orbital angular momentum singularities ensures that these nanoscale illumination patterns remain stable against perturbations that would normally destroy delicate interference effects, providing robust performance even in challenging biological environments where refractive index variations and scattering can corrupt conventional structured illumination approaches. Recent advances in imaging with structured beams have extended super-resolution capabilities beyond simple point scanning techniques toward wide-field methods that can capture entire cellular regions simultaneously while maintaining nanoscale resolution throughout the imaging field. These developments exploit sophisticated beam-shaping technologies including spatial light modulators and metasurfaces to create complex illumination patterns that encode spatial frequency information beyond the normal passband of optical systems, effectively expanding the numerical aperture through computational reconstruction methods. Machine learning algorithms now play crucial roles in optimizing beam patterns for specific imaging tasks, automatically designing orbital angular momentum distributions that maximize resolution enhancement while minimizing photo damage and acquisition time requirements. The combination of structured illumination with advanced image processing enables reconstruction of super-resolved images from multiple acquisitions with different beam parameters, achieving resolution improvements that approach the theoretical limits imposed by signal-to-noise ratios rather than diffraction physics. Applications in neuroscience have particularly benefited from orbital angular momentum enhanced microscopy, enabling visualization of synaptic structures, dendritic spines, and axonal transport processes at spatial scales previously accessible only through destructive sample preparation techniques that preclude observation of living neural tissue. The ability to track individual protein complexes and vesicles moving through neural circuits has revolutionized our understanding of synaptic transmission, plasticity, and pathological processes associated with neurodegenerative diseases. Live cell imaging of neural development now reveals the formation of connections and the migration of neural precursor cells with unprecedented clarity, providing insights into fundamental questions about brain development and regeneration that were previously impossible to address experimentally. Cell biology applications have exploited super-resolution orbital angular momentum microscopy to investigate subcellular structures including mitochondrial networks, endoplasmic reticulum organization, and cytoskeletal dynamics at scales where molecular interactions become directly observable through optical methods. The gentle nature of the technique enables long-term time-lapse studies of cellular processes without the phototoxicity that typically limits conventional super-resolution approaches, allowing researchers to follow individual molecules through complete functional cycles spanning hours or days. Recent studies have achieved simultaneous tracking of multiple molecular species labeled with different fluorophores, revealing complex interaction networks and temporal correlations that illuminate fundamental mechanisms of cellular function and regulation. Could the infinite ladder of orbital angular momentum states provide the key to building quantum computers so powerful they could simulate entire universes while simultaneously storing quantum information with perfect fidelity for geological timescales? Orbital angular momentum as a high-dimensional qubit transcends the fundamental limitations of traditional two-level quantum systems, offering access to exponentially larger computational spaces where single photons can encode hundreds or thousands of bits worth of quantum information through their helical phase structures and topological charge configurations. Unlike conventional qubits restricted to superpositions of 0 and 1 states, orbital angular momentum qubits exploit the infinite dimensional Hilbert space associated with integer biological charges to create quantum registers where individual particles carry enough information to represent entire classical databases or complex mathematical objects that would normally require vast arrays of traditional quantum bits. This dramatic enhancement in information density per particle revolutionizes quantum algorithm design by enabling more efficient implementations of quantum Fourier transforms, Shor's factoring algorithm, and quantum simulation protocols that exploit high-dimensional entanglement to achieve exponential speedups over classical computation. Quantum memory. Demonstrations have successfully stored and retrieved orbital angular momentum quantum states in atomic vapors, crystalline solids, and other material systems that can preserve quantum coherence for extended periods while maintaining the topological charge information essential for faithful quantum state reconstruction. Recent experiments have achieved storage times exceeding several minutes for high-dimensional orbital angular momentum states, demonstrating that complex quantum information can survive decoherence processes that typically destroy more fragile quantum systems within microseconds or milliseconds. The storage mechanisms exploit electromagnetically induced transparency, atomic frequency combs, or photon echo techniques that map the optical quantum state onto collective atomic excitations that behave as quantum memories capable of preserving both amplitude and phase relationships across multiple orbital angular momentum modes simultaneously. These achievements prove that high-dimensional quantum information can be reliably stored, manipulated, and retrieved on demand, providing essential building blocks for scalable quantum computing architectures that require long-term quantum memory for error correction and complex algorithm execution. Fault-tolerant quantum computation possibilities emerge naturally from the high-dimensional nature of orbital angular momentum systems, where quantum error correction codes can exploit the large number of available states to implement sophisticated error detection and correction schemes that surpass the performance of conventional approaches limited to two-dimensional qubit spaces. The mathematical structure of orbital angular momentum enables natural implementation of topological quantum error correction codes that protect quantum information through global properties of the quantum state, rather than local correlations that can be easily disrupted by environmental noise. Higher dimensional quantum codes achieve better distance properties and lower threshold error rates compared to traditional stabilizer codes, potentially enabling fault-tolerant quantum computation even in the presence of significant decoherence and operational imperfections that would render conventional approaches unusable. Vector vortex beams combine orbital angular momentum with polarization degrees of freedom to create hybrid quantum systems where individual photons simultaneously carry information in multiple independent channels, enabling implementation of quantum gates and quantum algorithms that exploit both spatial and polarization entanglement for enhanced computational power. These hybrid systems can generate exotic entangled states that exhibit correlations across different physical degrees of freedom, creating quantum resources suitable for universal quantum computation, quantum communication, and quantum sensing applications that require access to high-dimensional entangled states with specific symmetry properties. The non-separable nature of vector vortex beams provides natural protection against certain types of decoherence, while enabling new classes of quantum algorithms specifically designed to exploit the rich mathematical structure of combined spin and orbital angular momentum systems. Future prospects for quantum internet infrastructure depend critically on the ability to generate, transmit, and detect high-dimensional quantum states over intercontinental distances through both fiber optic networks and free space satellite links, applications where orbital angular momentum provides unique advantages in terms of information capacity, noise resistance, and compatibility with existing telecommunications infrastructure. Quantum repeater networks based on orbital angular momentum could enable truly global quantum communication by exploiting the high-dimensional nature of these systems to implement more efficient quantum error correction and entanglement purification protocols that maintain quantum coherence across multiple transmission hops spanning thousands of kilometers. The integration of orbital angular momentum quantum technologies with emerging quantum computing platforms including superconducting circuits, trapped ions, and neutral atom arrays promises to create hybrid quantum systems that combine the strengths of different physical implementations while mitigating their individual weaknesses through clever interface protocols and quantum state transfer mechanisms. These hybrid approaches could enable quantum computers that process information using orbital angular momentum while storing it in solid-state quantum memories, creating scalable architectures suitable for solving computationally intractable problems in cryptography, optimization, chemistry, and artificial intelligence that remain beyond the reach of even the most powerful classical supercomputers ever constructed. What happens when our most sophisticated mathematical theories encounter fundamental obstacles that seem to mock our deepest understanding of electromagnetic reality, revealing that even 3 decades after discovering orbital angular momentum, we still wrestle with mysteries that challenge the very foundations of physics itself? Even now, 30 years later, light continues to surprise us with new secrets as the gauge invariance problem exposes profound theoretical challenges in our attempts to separate spin and orbital angular momentum into distinct, physically meaningful components that remain well-defined, regardless of our choice of mathematical coordinate systems or electromagnetic potentials. The revolutionary 2025 no-go theorems, published by leading theoretical physicists, have shattered long-held assumptions about the separability of electromagnetic angular momentum, proving rigorously that any attempt to decompose the total angular momentum of massless gauge bosons like photons into intrinsic spin and orbital contributions necessarily fails to satisfy fundamental requirements of relativistic field theory. These mathematical proofs demonstrate that spin-orbit separation cannot simultaneously preserve Lorentz invariance, maintain gauge independence, and yield local expressions that remain physically meaningful under arbitrary coordinate transformations, forcing physicists to confront the uncomfortable reality that our intuitive pictures of spinning and orbiting photons may be fundamentally flawed. The theorems emerge from deep analysis of the representation theory of the Poincaré group, showing that massless particles with spin 1 exhibit mathematical structures that forbid the existence of well-defined position operators of the Newton-Wigner type that would be necessary for constructing meaningful orbital angular momentum in a covariant manner. Why separating spin and orbital angular momentum proves fundamentally challenging connects to the gauge freedom inherent in an electromagnetic theory, where the vector potential can be modified by adding the gradient of any scalar function without affecting observable electromagnetic fields or their physical consequences. This gauge freedom means that different choices of electromagnetic potentials can lead to different decompositions of the total angular momentum, making the separation between spin and orbital components appear arbitrary and unphysical, rather than representing genuine properties of the electromagnetic field itself. The mathematical formalism reveals that attempts to construct gauge-independent definitions of spin and orbital angular momentum necessarily involve non-local expressions that violate fundamental principles of locality and causality that form cornerstones of relativistic field theory. Gauge-dependent versus gauge-independent descriptions present an ongoing tension that pervades modern electromagnetic theory, where calculational convenience often requires working with specific gauge choices that simplify mathematical manipulations but may obscure the underlying physical content of the theory. The Coulomb gauge, Lorentz gauge, and radiation gauge each provide different perspectives on the same physical phenomena, leading to different decompositions of angular momentum that cannot all simultaneously represent fundamental aspects of reality. Recent theoretical investigations have explored whether certain combinations of spin and orbital contributions might remain gauge invariant even when individual components suffer from gauge dependence, seeking observable quantities that capture the essential physics while avoiding the mathematical pathologies that plague naive separation attempts. These efforts have led to new understanding of electromagnetic momentum and angular momentum in material media, where the presence of matter provides additional structure that can partially resolve the gauge ambiguities that plague vacuum electromagnetic fields. Recent theoretical progress has focused on identifying physically meaningful quantities that remain well-defined despite the fundamental obstacles revealed by the no-go theorems, developing new formulations of electromagnetic theory that emphasize observable consequences rather than attempting to decompose unobservable intermediate quantities into conceptually appealing but mathematically problematic components. Advanced approaches exploit the geometric structure of electromagnetic fields to define intrinsic characteristics that capture essential features of spin and orbital motion without requiring explicit separation into distinct contributions. These geometric methods utilize concepts from differential geometry and fiber bundle theory to construct gauge-invariant descriptions of electromagnetic angular momentum that respect both relativistic covariance and the fundamental constraints imposed by massless gauge theory. The remaining questions challenge our most basic assumptions about the nature of electromagnetic radiation and the relationship between mathematical formalism and physical reality, suggesting that light may possess aspects that transcend our current theoretical frameworks and require entirely new conceptual approaches to understand properly. Physics isn't finished with light, or light isn't finished with physics, as these fundamental mysteries continue driving theoretical advances that push the boundaries of our understanding while revealing new layers of complexity hidden within phenomena that initially seemed straightforward and well understood. The resolution of these deep theoretical problems may require revolutionary changes in our mathematical description of electromagnetic fields, potentially leading to new insights about the quantum nature of spacetime itself and the fundamental structure of physical reality at scales where classical concepts of particles and waves break down completely. Could orbital angular momentum provide the perfect probe for detecting how massive rotating objects drag spacetime itself into motion? And what secrets might twisted light reveal about the fundamental geometry of the universe when it spirals through regions where Einstein's curved spacetime becomes dramatically apparent? When light twists through the fabric of spacetime itself, the helical structures that encode orbital angular momentum experience subtle but measurable modifications that reflect the curvature and rotation of the gravitational field through which the electromagnetic waves propagate, creating unprecedented opportunities for testing general relativity and exploring astrophysical phenomena that remain inaccessible to conventional observational techniques. Orbital angular momentum in gravitational fields undergoes fascinating transformations that arise from the non-Euclidean geometry of curved spacetime, where parallel transport of the electromagnetic field vector around closed loops can result in net rotations that accumulate additional phase shifts beyond those predicted by flat space. Electromagnetic theory. The mathematical description requires sophisticated tensor calculus and differential geometry to account properly for how orbital angular momentum modes propagate through regions where spacetime curvature becomes significant, such as the vicinity of neutron stars, black holes, or other compact massive objects that create strong gravitational fields capable of measurably affecting electromagnetic radiation. Recent theoretical calculations have shown that orbital angular momentum beams passing near rotating black holes should exhibit characteristic modifications to their topological charge distributions, with different modes experiencing differential phase shifts that depend on both the mass and angular momentum of the gravitating body. Astrophysical implications for black holes present some of the most exciting possibilities for orbital angular momentum research, where observations of twisted light from accretion disks or relativistic jets could provide direct measurements of black hole spin parameters and space-time geometry in the strong field regime, where classical tests of general relativity become inadequate. The extreme gravitational fields surrounding stellar mass and supermassive black holes create conditions where orbital angular momentum modes experience dramatic frequency shifts, trajectory deflections, and topological charge mixing that encode information about the fundamental properties of these exotic objects. Theoretical models predict that orbital angular momentum beams generated in accretion disk environments should carry signatures of the Kerr metric that describes rotating black holes, potentially enabling new methods for measuring black hole masses, spins, and electric charges through analysis of the twisted light emission patterns. Advanced gravitational wave detectors combined with optical interferometry using orbital angular momentum could reveal correlations between space-time ripples and electromagnetic radiation during black hole mergers or neutron star collisions, providing complementary information about these cataclysmic events that neither technique could obtain independently. Frame dragging effects on twisted light represent one of the most subtle predictions of general relativity, where massive rotating objects literally drag space-time into motion around them, creating preferred directions for electromagnetic propagation that break the spherical symmetry normally associated with static gravitational fields. The lens of Thirring precession affects orbital angular momentum modes by causing their helical axes to precess around the rotation axis of the gravitating body, introducing time-dependent modifications to the topological charge that accumulate during propagation through the gravitomagnetic field. Laboratory measurements using gyroscopes and atomic interferometers have detected frame-dragging effects around Earth, but orbital angular momentum provides potentially much more sensitive probes because the helical phase structure creates extended lever arms that amplify small space-time rotations into measurable phase shifts. Satellite-based experiments using orbital angular momentum communication links could achieve unprecedented precision in measuring Earth's gravitomagnetic field, testing predictions of general relativity with accuracies that surpass current techniques while simultaneously providing practical benefits for high-bandwidth space communications. Potential applications in testing general relativity extend far beyond black hole astrophysics into fundamental questions about the nature of gravity itself, including searches for deviations from Einstein's theory that might indicate new physics beyond the standard model of particle physics and general relativity. Orbital angular momentum interferometry could detect gravitational waves through their effects on helical phase relationships, complementing laser interferometer observatories with entirely different systematic errors and sensitivity profiles that might reveal gravitational wave sources invisible to current detection methods. Modified theories of gravity that predict additional scalar or vector fields could leave distinctive signatures in orbital angular momentum propagation that differ from pure tensor gravity, enabling tests of alternative theories including scalar tensor gravity, extra-dimensional models, and quantum gravity phenomenology. Solar system tests using orbital angular momentum beams transmitted between spacecraft or ground-based observatories could measure relativistic effects, including gravitational time dilation, frequency shifts, and trajectory deflections with unprecedented accuracy, potentially revealing subtle deviations from general relativity that current techniques cannot detect. The combination of advancing orbital angular momentum technology with increasingly sophisticated theoretical understanding of relativistic electromagnetism promises to open new windows into fundamental physics while providing practical tools for navigation, communication, and scientific exploration throughout the solar system and beyond. How can electromagnetic waves carrying orbital angular momentum maintain their helical integrity while undergoing violent transformations that double their frequency, split into multiple daughter beams, or generate entirely new wavelengths through chaotic nonlinear interactions with matter? Nonlinear optics with orbital angular momentum reveals a hidden universe of electromagnetic phenomena where twisted light beams exhibit exotic behaviors that challenge our fundamental understanding of how photons interact with each other and with material media under extreme intensity conditions that drive optical responses far beyond the linear regime. Frequency conversion preserving orbital angular momentum represents one of the most striking demonstrations of topological protection in nonlinear optical systems, where second harmonics, generation sum frequency mixing, and difference frequency generation processes can double, triple, or otherwise modify the optical frequency while maintaining the exact helical phase structure and topological charge of the input beam. These phenomena occur when intense orbital angular momentum beams propagate through nonlinear crystals with carefully engineered phase-matching conditions that ensure efficient energy transfer between fundamental and harmonic frequencies while preserving the spatial mode structure through proper conservation of electromagnetic momentum and angular momentum. The mathematical description requires extending traditional nonlinear optics theory to account for the spatial complexity of helical beams, involving coupled wave equations that describe how different orbital angular momentum modes interact through the nonlinear polarization induced in the crystal lattice by the intense electromagnetic fields. Recent experiments have demonstrated frequency doubling, efficiency exceeding 50% for orbital angular momentum beams, proving that nonlinear conversion can be just as efficient for twisted light as for conventional Gaussian beams, while opening pathways to coherent light sources at wavelengths where direct laser emission remains challenging or impossible. Four-wave mixing with orbital modes creates fascinating possibilities for all optical signal processing and quantum state manipulation, where multiple input beams with different topological charges interact through third-order nonlinear susceptibility to generate output beams carrying algebraic combinations of the input angular momentum values. The conservation laws governing these interactions specify that the sum of topological charges among input photons must equal the sum among output photons, creating selection rules that determine which combinations of orbital angular momentum modes can participate in efficient nonlinear conversion processes. Advanced phase matching. Techniques using quasi-phase matching structures or photonic crystals enable precise control over these interactions, allowing researchers to design nonlinear devices that perform specific angular momentum operations, such as adding, subtracting, or exchanging topological charges between different wavelength channels. The potential applications include all optical quantum logic gates, orbital angular momentum beam splitters, and frequency converters that enable interfacing between different wavelength regions while preserving quantum information encoded in helical phase structures. Solitons and self-healing beams emerge from the interplay between nonlinear refractive index changes and diffraction effects in materials where intense orbital angular momentum beams induce local modifications to the propagation characteristics that can exactly compensate for normal beam spreading, or even reverse degradation caused by partial obstructions or phase distortions. Spatial solitons carrying orbital angular momentum maintain their helical structure over extended propagation distances that would normally cause significant beam degradation, creating robust communication channels for free space optical links operating under challenging environmental conditions. The self-healing properties arise from nonlinear focusing effects that concentrate energy back toward the beam axis while preserving the topological phase structure, enabling orbital angular momentum beams to reconstruct themselves after encountering obstacles or atmospheric turbulence that would permanently destroy conventional laser beams. Recent theoretical work has predicted exotic soliton solutions with multiple topological charges and complex three-dimensional structures that exhibit unprecedented stability and novel propagation characteristics impossible with linear beams. Recent progress in nonlinear vortex dynamics has revealed rich phenomena, including vortex splitting, merging and annihilation processes, that occur when orbital angular momentum solitons collide or interact through overlapping nonlinear media, creating opportunities for studying fundamental physics of topological defects in optical systems that serve as accessible analogues for similar processes in condensed matter, physics and cosmology. High-intensity orbital angular momentum beams can create persistent modifications to material properties, including permanent refractive index changes, induced birefringence, and even structural modifications at the microscopic level, enabling fabrication of three-dimensional optical circuits and waveguides with helical symmetry that guide twisted light with minimal loss. Conservation laws and selection rules governing nonlinear orbital angular momentum interactions provide fundamental constraints that determine which processes can occur efficiently, while revealing deep connections between electromagnetic angular momentum and the symmetries of nonlinear optical materials, suggesting that careful engineering of crystal structures and quasi-phase matching patterns could enable novel device functionalities that exploit the topological protection of orbital angular momentum for robust nonlinear optical processing applications. Could we be approaching a technological singularity where machines process information using the infinite complexity of twisted light, creating artificial intelligences that operate with quantum mechanical sophistication while remaining stable at room temperature? As our journey through the spiral world of light comes to rest, let's glimpse what tomorrow might bring as integrated photonic circuits with native orbital angular momentum generation emerge from research laboratories into practical applications that will reshape computing, sensing, and communication technologies throughout the next decade. These revolutionary devices exploit advances in silicon photonics manufacturing to create chip-scale orbital angular momentum sources, processors, and detectors that eliminate the bulk optical components currently required for twisted light applications while achieving unprecedented performance, reliability, and cost-effectiveness. The integration process involves etching microscopic spiral structures directly into silicon waveguides, using electron beam lithography and reactive ion etching, techniques borrowed from semiconductor manufacturing, creating helical optical pathways that naturally generate orbital angular momentum without requiring external conversion elements or precise optical alignment. Advanced foundry processes enable mass production of these integrated circuits using the same fabrication infrastructure that produces conventional microprocessors, promising to drive costs down to consumer electronics levels while maintaining the precision and sophistication needed for quantum information processing applications. Room temperature quantum devices represent perhaps the most transformative development on the horizon, where orbital angular momentum systems operating at normal environmental temperatures could eliminate the expensive cryogenic cooling systems that currently limit quantum technologies to specialized laboratory environments and prevent widespread commercial deployment. The topological protection inherent in orbital angular momentum states provides natural resistance against thermal decoherence that typically destroys quantum coherence within microseconds at room temperature, enabling quantum information processing systems that maintain their quantum properties in normal office or laboratory environments without sophisticated environmental isolation. Recent theoretical work suggests that carefully engineered orbital angular momentum qubits could maintain quantum entanglement and superposition for milliseconds or even seconds at room temperature, sufficient for implementing practical quantum algorithms and quantum communication protocols without requiring expensive cooling infrastructure. The combination of room temperature operation with integrated photonic implementation promises to democratize quantum technology by making it accessible to researchers, engineers, and eventually consumers who lack access to specialized facilities with cryogenic capabilities. Orbital angular momentum-based quantum sensors and gyroscopes exploit the sensitivity of helical phase structures to rotational motion and magnetic fields to achieve measurement precision that surpasses classical sensors by orders of magnitude, while maintaining compact form factors suitable for portable applications. These devices detect minute changes in topological charge or phase relationships that occur when orbital angular momentum states interact with gravitational fields, magnetic fields, or rotational acceleration, converting physical perturbations into measurable optical signals with quantum-limited sensitivity. Military and civilian navigation applications could benefit enormously from orbital angulars, momentum gyroscopes that provide accurate positioning information even when GPS signals become unavailable or compromised, enabling autonomous vehicles and aircraft to maintain precise navigation capabilities in challenging environments. Medical applications include ultra-sensitive magnetometers for brain imaging and early disease detection, where orbital angular momentum sensors could detect biomagnetic fields associated with neural activity or metabolic processes with spatial resolution and sensitivity, impossible using conventional techniques. Optical neural networks using structured light represent a paradigm shift toward computation systems that process information using the physical properties of electromagnetic waves rather than electronic switching operations, potentially achieving computational speeds limited only by the speed of light, while consuming dramatically less power than conventional digital processors. These systems exploit the parallel processing capabilities inherent in orbital angular momentum beams, where different topological charges can carry independent information streams that undergo simultaneous mathematical operations through carefully designed optical elements including nonlinear crystals, spatial light modulators, and integrated photonic processors. Machine learning algorithms implemented using orbital angular momentum could process visual recognition, natural language understanding, and pattern-matching tasks with unprecedented efficiency, while maintaining the fault tolerance and adaptability that characterize biological neural networks. The prospect of computers that think with twisted light suggests artificial intelligence systems that combine the best aspects of quantum and classical computation, using orbital angular momentum to implement quantum algorithms for optimization and search, while maintaining classical reliability for routine data processing operations. Advanced applications under development include orbital, angular momentum-based telepresence systems that transmit not just visual and auditory information, but also tactile and spatial context through high-dimensional quantum states, creating immersive virtual reality experiences that approach the fidelity of direct sensory perception. What fundamental aspects of electromagnetic radiation continue lurking beyond our current understanding, waiting to revolutionize physics once again as orbital angular momentum did 30 years ago? And could light possess infinite layers of complexity that humanity has only begun to discover? The deeper questions emerging from 3 decades of orbital angular momentum research point toward hidden properties of light that may dwarf our current knowledge in the same way that twisted photons initially seemed impossible, until scientists learned to recognize their signatures dancing before our eyes in laboratory experiments. Every answer births 10 new questions as researchers probe the mathematical structures underlying electromagnetic fields, discovering connections between seemingly unrelated phenomena that suggest light carries information and exhibits behaviors far more sophisticated than any theory currently predicts or any experiment has yet revealed. The search for additional hidden properties focuses on higher-order field correlations, multi-photon entanglement patterns, and topological phases that might encode information in spatial, temporal, or frequency domains that conventional detection methods cannot access. Recent investigations into electromagnetic field tensor properties have revealed potential for carrying information in field gradients, curvature tensors, and higher-order derivative relationships that exist independently of intensity, phase, and polarization measurements that currently define our complete characterization of optical states. Advanced quantum field theory suggests that electromagnetic radiation might possess emergent properties arising from collective behaviors of many photons that remain invisible when studying individual particles, but become apparent in carefully orchestrated ensemble measurements involving correlated detection across multiple spatial locations and time intervals. Connection to fundamental symmetries in nature reveals deep relationships between orbital angular momentum and the mathematical structures that govern particle physics, cosmology, and the geometry of spacetime itself, suggesting that twisted light might serve as a macroscopic manifestation of symmetry principles that operate throughout the physical universe. The rotational symmetries underlying orbital angular momentum mirror the gauge symmetries that determine electromagnetic interactions, weak nuclear forces, and strong nuclear forces in the Standard Model, hinting that helical electromagnetic fields might provide experimental access to fundamental physics that currently requires high-energy particle accelerators to investigate. Supersymmetry theories predict relationships between bosonic and fermionic particles that could manifest in optical systems where orbital angular momentum photons exhibit behaviors analogous to spin-half particles, potentially enabling tabletop experiments that test theories normally requiring cosmic ray energies or super collider facilities. The topological protection of orbital angular momentum resembles mechanisms proposed for protecting quantum information in topological quantum computers, suggesting deep connections between electromagnetic vortices and the exotic states of matter that could enable fault-tolerant quantum computation through braiding operations in higher dimensional spaces. Role in quantum field theory and particle physics continues expanding as theorists discover that orbital angular momentum provides natural laboratory systems for studying phenomena, including spontaneous symmetry breaking, phase transitions, and collective quantum effects that normally occur only in condensed matter, systems, or cosmological contexts. Vacuum fluctuations in electromagnetic fields might carry orbital angular momentum signatures that reveal information about virtual particle processes, zero-point energy distributions, and the quantum structure of apparently empty space, potentially providing new insights into dark energy, cosmological inflation, and the fundamental nature of the vacuum state. High-energy physics experiments using orbital angular momentum could probe the electromagnetic properties of exotic particles, including magnetic monopoles, axions, and other hypothetical entities predicted by theories beyond the Standard Model, exploiting the sensitivity of helical photons to magnetic and electric field configurations that would remain invisible to conventional electromagnetic probes. The possibility of electromagnetic duality relationships connecting electric and magnetic orbital angular momentum suggests that twisted light might reveal hidden aspects of electromagnetic theory that have remained obscured since Maxwell first wrote his famous equations over 150 years ago. Potential applications we haven't imagined yet span disciplines from archaeology and geology to consciousness research and interstellar communication, where orbital angular momentum might enable entirely new categories of sensing, imaging, and information processing that transcend current technological limitations. Archaeological surveys using orbital angular momentum could detect buried structures through subtle electromagnetic signature analysis that reveals subsurface features invisible to ground-penetrating radar or conventional remote sensing techniques. Geological exploration might exploit orbital angular momentum sensitivity to mineral compositions, crystalline structures, and fluid movements that indicate valuable resource deposits or earthquake precursor phenomena. The prospect of consciousness-light interactions through orbital angular momentum suggests possible connections between electromagnetic field structures and neural processes that could illuminate fundamental questions about awareness, memory, and the relationship between physical and mental phenomena. Interstellar communication using orbital angular momentum could enable transmission of complex three-dimensional information across cosmic distances while maintaining signal integrity against galactic magnetic fields, cosmic ray interference, and other sources of electromagnetic noise that limit conventional radio astronomy and space communication systems. Could the spiral patterns we carefully craft in earthbound laboratories actually mirror cosmic choreography that has been unfolding across galactic distances for billions of years, carrying information about the universe's deepest secrets through helical light, beams that connect our small world to the grandest scales of existence? The cosmic perspective reveals how orbital angular momentum transcends terrestrial applications to become a fundamental tool for astronomical discovery, where the same spirals we create in labs may dance between distant stars as natural phenomena that encode information about stellar magnetic fields, planetary atmospheres, and the large-scale structure of space itself. Astronomical observations using orbital angular momentum represent a revolutionary approach to extracting information from starlight that has traveled unimaginable distances through interstellar and intergalactic space, potentially carrying twisted signatures that reveal physical processes occurring around distant suns, black holes, and other exotic objects throughout the cosmos. Recent theoretical work suggests that magnetic fields surrounding stars and galaxies could naturally generate orbital angular momentum in electromagnetic radiation through plasma interactions, creating helical patterns in light that astronomers could detect using specialized instruments designed to analyze the topological charge content of astronomical sources. The prospect of measuring orbital angular momentum in cosmic radiation opens entirely new observational windows that complement traditional techniques based on intensity, spectroscopy, and polarimetry, potentially revealing phenomena that remain invisible to conventional astronomical methods while providing unprecedented insights into the electromagnetic environments that exist throughout the universe. Coronagraphy using optical vortices for exoplanet detection represents one of the most promising near-term applications, where the central darkness characteristic of orbital angular momentum beams provides perfect nulling capabilities for suppressing brilliant starlight while preserving the faint signals from orbiting planets that would otherwise remain completely overwhelmed by their parent star's glare. Traditional coronagraphs struggle to achieve the contrast ratios exceeding 1 billion to 1 that are necessary for direct imaging of Earth-like exoplanets, but orbital angular momentum nulling techniques could theoretically achieve the performance needed to photograph rocky worlds orbiting within habitable zones around nearby stars. The topological protection of orbital angular momentum singularities ensures that the central null remains stable against atmospheric turbulence and instrument imperfections that would normally destroy conventional coronagraph performance, enabling ground-based telescopes to achieve space-based image quality for exoplanet detection and characterization. Advanced coronagraph designs incorporating multiple orbital angular momentum modes could simultaneously null multiple stellar sources in binary or multiple star systems, enabling detection of planetary systems that would remain inaccessible using traditional techniques that can only suppress single-point sources. Stellar interferometry with structured light promises to revolutionize high-resolution astronomy by combining orbital angular momentum beams from multiple telescopes to create synthetic apertures with unprecedented angular resolution and sensitivity to spatial structures that conventional interferometry cannot detect. The helical phase relationships in orbital angular momentum provide additional baseline measurements that complement traditional interferometric observables, potentially enabling reconstruction of stellar surface features, magnetic field topologies, and circumstellar disk structures with detail approaching that achieved by spacecraft visiting our solar system. Multi-telescope arrays utilizing orbital angular momentum could achieve effective apertures spanning continents or even space-based configurations that surpass any conceivable single-mirror telescope, while maintaining the sensitivity needed for studying the faintest and most distant objects in the observable universe. The combination of orbital angular momentum interferometry with adaptive optic systems could enable real-time imaging of stellar surfaces, sunspot cycles on distant stars, and the dynamics of stellar atmospheres with temporal and spatial resolution that transforms stellar astronomy from a statistical science into a detailed observational discipline comparable to solar physics. Possible role in understanding cosmic magnetic fields emerges from the sensitivity of orbital angular momentum to magnetize plasmas that pervade interstellar and intergalactic space, potentially providing direct measurements of magnetic field strength and topology in regions where conventional techniques fail due to insufficient signal levels or overwhelming background contamination. The interaction between twisted light and cosmic magnetic fields could reveal information about galactic dynamos, magnetic reconnection process, and the origin of large-scale magnetic structures that influence star formation, cosmic ray propagation, and the evolution of galaxies themselves. Radio astronomy observations using orbital angular momentum might detect helical signatures in pulsar radiation, providing insights into neutron star magnetic field configurations and plasma physics under extreme conditions that cannot be replicated in terrestrial laboratories. The prospect of orbital angular momentum astronomy extends beyond our own galaxy to cosmological distances, where twisted light signatures could reveal information about dark matter, dark energy, and the fundamental structure of space-time during the early universe. When cosmic microwave background radiation first began its journey toward Earth, carrying potential orbital angular momentum signatures from primordial magnetic fields and gravitational waves that shape the cosmos we observe today. What profound lessons about human curiosity and scientific discovery can we draw from the remarkable journey that began with a simple observation of unusual donut-shaped patterns in a Leiden laboratory, and has grown into a revolution that touches quantum computing, astronomical observation, and our fundamental understanding of reality itself? As we reach the gentle conclusion of our exploration through the spiral world of light, we find ourselves transformed by witnessing how 33 years of patient investigation have revealed layer upon layer of electromagnetic complexity hidden within phenomena that initially seemed like mere optical curiosities deserving only a footnote attention in specialized physics journals. The beauty of incremental discovery shines through every chapter of this ongoing story, where each breakthrough built carefully upon previous insights while opening doorways to questions that no one had previously thought to ask, demonstrating the profound truth that scientific understanding advances not through sudden revelations, but through countless small steps taken by researchers who remain curious about details that others might dismiss as unimportant. Alan's team could never have imagined that their careful measurements of laser mode patterns would eventually enable quantum communication networks spanning continents, super-resolution microscopy that reveals the inner workings of living cells, or astronomical instruments capable of directly imaging planets orbiting distant stars. Yet each of these applications traces its lineage directly back to that February evening when something unexpected appeared in their optical setup. How simple curiosity about donut-shaped beams led to a quantum revolution illustrates the unpredictable nature of scientific progress, where fundamental advances often emerge from investigations motivated by pure intellectual interest, rather than specific technological goals or commercial applications. The researchers who first studied orbital angular momentum were driven by the desire to understand why light behaved in ways that contradicted their theoretical expectations, pursuing knowledge for its own sake without anticipating that their discoveries would eventually revolutionize multiple fields simultaneously. This pattern repeats throughout scientific history, where basic research into seemingly esoteric phenomena later enables transformative technologies that reshape human civilization in ways that pure science fiction could never anticipate. The mathematical elegance underlying orbital angular momentum continues inspiring new generations of physicists, engineers, and applied researchers who find beauty in the infinite spiral structures that light can adopt while maintaining perfect stability across cosmic distances and geological timescales. Today's graduate students and postdoctoral researchers carry forward this tradition of curiosity-driven investigation, pushing the boundaries of what seems possible while remaining humble before the vastness of what remains unknown about electromagnetic radiation and its role in the cosmic symphony that surrounds our small blue planet. Your personal invitation for continued learning extends far beyond passive consumption of scientific content toward active engagement with the ongoing discovery process, whether through pursuing formal education in physics and engineering, participating in citizen science projects that contribute to research, or simply maintaining the sense of wonder that drives all meaningful scientific inquiry. The questions explored throughout our journey together represent just the beginning of a much larger conversation about light, quantum mechanics, and the fundamental structure of reality that will continue evolving as technology advances and human understanding deepens. Each person who develops curiosity about these topics becomes part of a global community dedicated to unraveling nature's mysteries, while applying that knowledge to benefit humanity through improved communication, computation, medicine, and exploration capabilities. The scientific enterprise thrives when people from diverse backgrounds bring fresh perspectives to established problems, often discovering connections and possibilities that specialists might overlook due to their deep immersion in technical details. Your gentle engagement with this content, whether through subscribing, sharing insights, or pursuing further learning, helps support the broader ecosystem of science communication that makes advanced research accessible to wider audiences, while inspiring the next generation of researchers who will continue pushing these frontiers forward. The feedback and questions from curious learners often highlight aspects of scientific work that deserve greater attention, or suggest new directions for investigation that professional researchers might not consider without input from fresh viewpoints. Light will continue its eternal dance, twisting and turning through space and time, carrying its secrets at the speed of forever, while waiting patiently for human ingenuity to develop new methods for decoding the information embedded within electromagnetic fields that connect our local experiences to cosmic phenomena spanning distances and timescales that challenge imagination. The spiral patterns that dance through laboratory beams today will inspire discoveries tomorrow that we cannot yet envision, ensuring that the story of orbital angular momentum remains unfinished, inviting future generations to add new chapters filled with insights that will once again transform our understanding of light, matter, and the elegant mathematical principles that govern both quantum mechanics and cosmic evolution across the infinite universe that surrounds us with its eternal mysteries.